Okay, this is Physical Science 102, Chapter 20 in your textbook, Atmospheric Effects. We've already looked at the characterization of the atmosphere in Chapter 19. Now we want to look at some of the dynamics of the atmosphere. So let's begin by sharing the PowerPoints. Right. And there we go. Okay. Make some adjustments on my end here. All right. Atmospheric effects. As I mentioned a few seconds ago, Chapter 19 considered concepts of the structure of the atmosphere and some terminology that we may use. But in Chapter 20, we're going to look at these structures and how they combine in some way to form what we might call weather. And we're also going to look at the difference between weather and climate. Okay, as a review, the lower atmosphere, the troposphere, is where weather happens. By and large, some types of weather that develop in the troposphere can extend into the next layer, the stratosphere. But the weather itself develops in the lower section of the atmosphere, the troposphere. We're going to look at the movements of large air masses and how they interact when they come into contact with one another, and what type of weather they produce. These large air masses can actually move great distances. In fact, during the winter months in the northern hemisphere, the weather is dominated by movements of cold air masses from the Arctic regions, and they move down into the temperate zone and bring with them these cold air masses and other things that come with them, like moisture content and any types of disturbances they'll bring with them. And depending on how fast they're moving, they can influence the local weather for quite some time. Now, the controlling factors that dictate the movement of these air masses are globally distributed. And it's important to understand how the not just the structure of the atmosphere, but how temperature differences and pressure differences in the atmosphere and the movement of the Earth itself affect these air masses, how they form and how they interact. So, first concept has to do with condensation. So we're talking about moisture here. When we say condensation, what we're talking about is the change of phase of water in the atmosphere from gas phase, vapor phase, into liquid phase. That's condensation. And in these air masses, condensation occurs when local temperatures in the air mass reach what we call the dew point. The dew point, I'm not sure if we've mentioned that before, but I'll mention it again. The dew point is that temperature at which the air mass becomes saturated, and any temperature at or below the dew point will cause water vapor to condense. So it's a temperature thing. The dew point is a temperature. There are occasions, though, where the water vapor temperature, the dew point can be, the temperature of the atmosphere can dip below the dew point, and the water still remains in the vapor phase. In that case, we call the air mass supercooled, and consequently it becomes supersaturated because it holds more moisture in the vapor phase than you would expect at that temperature. And that happens quite often, especially in certain types of air masses where the circulation is very rapid. Now, when these condensates form in air masses, and typically you're going to find, in fact, when water vapor condenses and forms these droplets, that's where you get clouds. That's what makes a cloud. The condensation forms the cloud. But the water droplets don't form from the vapor directly into the liquid phase without something to form around. They need a seed of some kind. Now, these nuclei, as we call them, that allow the water vapor to condense can be almost anything. They can be, and they're generally hygroscopic. And what we mean by hygroscopic is they attract moisture. They can be fine particles of dust that's blown up into the atmosphere. They can be smoke produced either naturally or artificially by man, by burning things. Smoke, soot, right? Partially combusted materials form soot. They can be salt spray, in fact. They could even be bacteria. Bacteria have been found at extreme high altitudes by sampling the air masses at different levels. Bacteria have been found at places you would not expect them, very high altitudes, and they can serve as hygroscopic nuclei. So condensation requires these nuclei. One of the benefits of this fact is that when the droplets form, they trap these particles that are in the atmosphere. And when the droplets get big enough, then they can fall through the atmosphere as rain or as some other form of precipitation. They have a cleansing effect. So if there are insufficient numbers of these airborne hygroscopic particles to serve as nuclei, then you can decrease the temperature to below the dew point, and you won't get, this is one of the reasons that you won't get condensation, because there are not nuclei available. Okay. What is precipitation? Well, precipitation is the natural outcome of condensation when you get condensates that are large enough size droplets so that they can fall through the atmosphere. If they're too small, then natural currents in the atmosphere will keep them mixed up and they won't drop out of the cloud. In other words, they're easily suspended. So you need a certain minimum size droplets, and that depends on the types of air currents that you have. If the air currents are very strong and the updrafts are very strong, then these droplets may be suspended and continue to form and get larger and larger until they finally get big enough to where they can overcome those updrafts. Two processes, the theory goes, are responsible or potentially responsible for increasing the size of droplets to this maximum size, to the minimum size where they will fall as precipitation. Right? One is called coalescence. The other is called the Bergeron process, and we're going to describe those in just a second. First, coalescence. This is the older theory. Coalescence says that the formation of these larger drops is by the process of impacts of smaller drops that stick together. So they coalesce into larger drops. And that seems intuitively correct. But the question is, does the experimental evidence support it? Okay. It does occur. That has been proven. Coalescence does occur. But it occurs more often when the droplets are pretty large to begin with. So the question is, how do they get to be that large? So they're large enough to coalesce. The minimum size for coalescence to take place is droplets that are 100 micrometers in diameter. And remember from, maybe it was the first semester, we studied units of measure. And units of measure, the standard of length is the meter, right? So if we prefix that with some letter, in this case, the Greek letter mu, that modifies the size of the unit, remember? So if this is a meter, the mu stands for 10 to the minus 6 times the meter. So the micrometer, the micrometer, is 1,000,000 times smaller than a meter. So if this a meter is this big, then the micrometer is going to be too small to see. So the size of these drops needs to be at least 100 micrometers across in order for coalescence to take effect. This process, the Bergeron process, was proposed by a Swedish meteorologist, that is, a person who studies weather. And now it's believed that this is the more common process at work when precipitation forms. It is more important. The theory behind this was developed in Norway. The meteorologist was Swedish, but he was working in Norway at the time at this particular institute, the Bergen Geophysical Institute. Sometimes the process is called the cold rain process. And there are essentially three processes, three essential components that are required for this process to form the precipitation. First, you need ice crystals. in the upper portion of the cloud. So if you get high enough, remember we studied temperature changes through these different layers of atmosphere. If you get high enough, then the temperature drops so low that the condensation is actually it's actually a process of deposition, where you take the gas and you make a solid out of it around these particles. But the ice crystals form in the upper part of the cloud, right? And the vapor in the lower part of the cloud becomes supercooled. In other words, it becomes colder than the dew point. Okay, those two processes are required. Then the third process is there must be mixing, agitation, right? Updrafts and downdrafts constantly in the cloud. That brings the ice crystals in contact with this supercooled vapor. And when it does that, then it causes all of that moisture that's just sitting there waiting to condense. By the way, a supercooled vapor is very unstable. All it needs is just a spark of something to cause it to condense, and then it just happens rather quickly. So the agitation brings these ice crystals into contact with the supercooled vapor in the lower portion of the cloud, and there you have it. These ice crystals serve as nuclei, further nuclei for the moisture in this supercooled portion of the cloud. That's the Bergeron process. And this is an illustration of it. So in the upper part, you have the ice crystals, lower part, you have the supercooled vapor, and with mixing, you get these ice crystals that come down, and they cause a rapid cooling in a microenvironment around themselves, which causes the moisture to condense around them. And when it does, it causes the condensation to occur, but at the same time, the ice crystal melts. So that's why you don't have a mixture of ice crystals and water falling out of the cloud at the same time. It's liquid water by the time it reaches the ground. Okay, so this, let's see. All right. I got ahead of myself. When these ice crystals mix with the supercooled water, the water vapor, actually, this is kind of a solid coalescence. You get more and more ice formed around the small crystal, and you get the large ice crystals, which then are large enough to fall. But as they fall, then they melt and form the water droplets that are large enough to overcome any drafts or mixing effects. And then coalescence can also take place, because once these ice crystals grow, fall, and melt, then on their way down, they can coalesce. So we don't throw away coalescence altogether simply because we have a new process, the Bergeron process. The Bergeron process gives us starting points for the coalescence to occur. Now, with this knowledge, we've also been able to initiate rain from clouds that would normally just pass over a region and not drop any rain. In other words, you might have clouds in the sky and you've been in a drought for months, say. You would like for that cloud to drop what moisture it contains. And rainmaking is is a respected scientific process. So with the knowledge of the Bergeron process, we can cause the coalescence, not coalescence, the deposition of moisture in the form of ice crystals. We just have to provide it with nuclei. So one of the possibilities is you fly high over the cloud or through the top parts of the cloud, and you spread silver iodide crystals, very small crystals. And if you investigate them under a microscope, you see that they have a similar structure to ice. So they're very good seed materials to form these ice crystals. And once you get the ice crystals going, the rest just follows through with the Bergeron process. They've also used small particles of dry ice or frozen carbon dioxide. And what that does, since carbon dioxide, solid CO2, dry ice, is at a temperature of minus 78.5 degrees Celsius, it's very cold. So if you drop that into the cloud, you get these ice crystals that would normally form on their own. There may be some up there, but this makes a lot of them form. And then once you get that process started, then the Bergeron takes over. And there's rapid cooling of this dry ice. You know, if you've ever seen dry ice before, if you take a chunk of it and just throw it on the ground, it doesn't turn to liquid. It doesn't make liquid carbon dioxide. It goes straight from solid to gas, which is called sublimation. And as it sublimes, it extracts heat from its surroundings, right? Because if it's going to go from minus 78 to room temperature, 20 degrees or 25 degrees Celsius, it can't get there unless it absorbs heat. So it takes heat from its surroundings, and that's what it does in the cloud. It cools the cloud rapidly to very low temperature, and that's what triggers the Bergeron to occur. Okay. That is, we focused on forming liquid precipitation from clouds, but that's not the only form that it can take. It depends on primarily the temperature of the temperatures that are in the cloud and the air mass to determine what type of precipitation falls. It could occur as rain, we've talked about before. It could be snow, right? If those ice crystals fall and they build up in size, but the temperature is still too cold to melt, then they may fall as snow, or they may fall as sleet, depending on the conditions that are predominant in the cloud itself. They may fall as hail. If the snow or the sleet falling experiences strong updrafts, it'll drive that sleet or snow back up into the cloud, and it gets bigger. And it starts to fall, and another draft takes it up again. And several cycles like that can occur, and the hail picks up more ice and gets bigger and bigger and bigger. My father used to tell me stories about growing up in Nebraska. And in Nebraska, he said, these thunderstorms would come by, even in the summer. They would blow through, and you would get hail the size of baseballs and some softballs, huge. And when they fall from several thousand feet, they can do some damage. In fact, he worked on a ranch, and they would kill cattle out in the field. They just smack them in the head, and they would drop. So if you saw one of these storms coming, and your livelihood was at risk, you would take those cattle and get them under cover. Okay, other types of precipitation, right? You don't have to have a cloud to produce some type of precipitation. You can get dew forming on cool surfaces overnight, particularly. As the temperature drops, then the surfaces form as the seed for accumulation of some condensate. You can form fog. And fog is basically just a cloud that's on the ground. Conditions have to be just right for these tiny droplets to form, and you have a cloud on the ground level. Rain is the most common in our latitudes. In the lower and middle latitudes for us, subtropical regions, well, actually tropicals too, and the middle latitudes, rain predominates. And in the middle latitudes where we're located, the seasonal changes dictate what type of precipitation to expect. If the dew point is below 0 degrees Celsius, you can expect snow to form. If you've ever looked at a snowflake, you'll see that they all have 6 sides. And that is an indicator for the microscopic structure of the snow, of the ice. Ice forms these hexagonal patterns too, but it's not as obvious. The snowflake gives you an obvious window into the way ice forms. So when liquid water condenses and freezes, you have the like that, and like let's see, like this. So there's a water molecule. It's bent, right? And this is a slightly positive side, and this is a slightly negative side. And as you cool it down, it can form intermolecular bonds between water molecules. Well, they prefer to do this. They will go like that and form a slight bond there because this is positive and that's negative. This is attached to that oxygen, and that hydrogen is out here free. And this one attaches to another hydrogen. Excuse me. There. And there's an oxygen, and there's a hydrogen. And then this one will have an oxygen here, a hydrogen there. This is a covalent bond that we studied in chemistry. And this is an intermolecular bond that's weaker. And then we have another one here, like that. So you get 1, 2, 3, 4, 5, 6. You get the 6-sided structure of ice, and you see that in the snowflake. Interestingly enough, ice is less dense than liquid water, which is, and the reason for it is, when water is free to move around in the liquid form, it doesn't form these structures. But when it forms these structures, they have to spread out a little bit in order to make this empty space in that hexagonal form. And that empty space increases the volume for the same mass. And remember when we studied density, density is mass per unit volume. So you increase the volume, you decrease the density. So when water freezes, it becomes less dense than the liquid. That's why ice floats in water. Okay. So, when does sleet form? Well, it falls directly from the cloud as ice pellets. It forms not directly from, well, it does form when rain freezes before it hits the ground. So typically what happens is it starts its journey as liquid water. But remember, these air masses, when they collide, are at different temperatures. So if the rain falls from a cloud as water and it passes through a neighboring air mass that is colder, less than 0 degrees Celsius, then that ice droplet will freeze, and that makes sleet. Whereas snow actually forms in the cloud and falls. Okay, so here's a discussion of hail. I mentioned it before. How do we know that large spheres of hail form in layers? They go up, add some more ice, come down, wind blows them back up, add more ice. Because if you cut through one, you will actually see the layers. Here we've cut these, this picture is of hail that's been cut in half, and you can see the layers that have formed in the hailstones. That's an indication of the fact that they've gone up and down in these drafts, picking up more ice as they go. Oh, and they tend to form in very strong thunderstorms. And that's necessary for 2 reasons. You get these strong thunderstorms, the cumulonimbus clouds, they stretch way up toward the top of the troposphere and very cold. And they have very strong winds. So these strong winds drive the condensate up into the cold region, makes ice, falls down, drafts pick them up again. You need very strong winds to make these large hailstones. Okay, dew forms when moisture in the air condenses on any surface. And you can see that any time of year. Even in the summer, you can see. It just depends on, is there moisture in the air sufficient? And does the temperature at night drop low enough to drop below the dew point for the air mass at that time? This dew point is not fixed. The dew point depends on how much moisture is in the air, because all you need to do is get the temperature cold enough so that now there's too much moisture for the air to hold, and it drops out as some form of precipitation. In this case, it condenses on things like blades of grass, the windshield of your car. If it gets cold enough, this dew can come out and be deposited as frost. Now, when this occurs, we're talking about going directly from gas to solid, and that's a process called deposition. And the point here is that frost is not frozen dew. It doesn't deposit in this case, on the rows. It doesn't deposit as a liquid and then freezes. It actually goes from gas to solid. It goes from the gas phase, the vapor phase, to the solid phase on that surface. That's deposition. Deposition is the opposite of sublimation. If you go from solid to gas, like dry ice, that's the opposite direction for deposition, is sublimation. Okay, let's talk a little bit about air masses. Weather, we must have defined weather and climate already. I think we did in chapter 19. Weather is a local phenomenon over short periods of time. Climate covers broader areas and over longer time periods. That's the basic difference between weather and climate. So we're talking about weather here. Localized events are largely due to the movement of these air masses across the country. Any area of the country. The air mass itself, we haven't actually defined the air mass, is a large body of air that typically takes on the characteristics of the land over which it moves. So if the air mass forms in the Arctic region during the winter, it's going to be cold, right? The ground, the surfaces are cold, and it gives up some of its heat to the earth as it moves across it. And each air mass that forms is easily distinguished from the air that surrounds it, the neighboring air, which also may be considered an air mass. When we describe an air mass, we're typically, we characterize it typically in terms of its temperature and moisture content. How much moisture is in the air and what's the temperature? So when the air mass remains over a certain area for an extended period of time, there's a chance for it to acquire characteristics from the land mass. Actually, these air masses can form over water too, right? They can form over large lakes or over oceans, smaller bodies of water, any size. And this is called the source region, right? It's the region of land or water that donates its characteristics to the air mass that's above it. So you would expect that if the ground is cold, the air mass will become colder. Or if the ground is saturated with water, then it will give up moisture to the air mass, and the moisture content in the air mass will increase. Or if it forms over water, definitely it will likely become saturated for that temperature. And as the air mass moves out of that region, for one reason or another, it will carry those physical characteristics with it, moisture and temperature predominantly. Now, we haven't said anything about air pressure. Air pressure, we think, is derived from these two characteristics, temperature and moisture content. So we haven't forgotten air pressure. It's just that it's more or less a derived characteristic. So these air masses I mentioned earlier can be derived from movement over different surfaces. They can be land or sea. They can be warm or cold. And the land can either be dry or saturated. And just as an interesting point, the land mass over which the air moves doesn't have to be perfectly flat, right? The Rocky Mountains, for instance, right? Air can move in off of the Pacific across the western states, and it runs smack into these mountains. Well, what's it going to do? It can't go through the mountains, it has to go up. So if it's moving in that direction against the mountains, and the air mass is moving like this, what happens to air when it increases in altitude? Generally speaking, the temperature decreases. So it goes up. We decrease the temperature. What does that mean? It gets too cold for the moisture that it holds. It holds a lot of moisture because it came off the ocean. So when it hits these mountains and goes up, it decreases in temperature. And eventually, the temperature decreases below the dew point for that air mass. And when that happens, you get precipitation. So that's why on this side of the mountain, you get an accumulation of water or snow, depending on the season. And on this side, moisture has been extracted from that air mass, and on this side, it gets dry. Okay? And it starts down and warms up. That's why, where is Death Valley in California? It's on the eastern side of the Rocky Mountains. It's over here. Like, Death Valley. It's very dry and very hot because all the moisture has been extracted from the air mass as it moves across the mountains. So the point is, air masses can originate over land or over water, and when they move, they respond to the terrain over which they're moving. Okay, we've got abbreviations. So when meteorologists identify air masses, one of the symbols they use determines over what surface did this air mass form. Is it over large body of water, like the oceans, in which you give it an M for maritime, or does it form over large land masses, and we give it a small c for continental? Those are the two divisions. Is it over land or is it over sea? Maritime sea, continental land. Then we also want to identify, where did it originate? Was it in the Arctic region, or was it even further? Was it in the polar region, right? At the North Pole or at the South Pole? Or did it form over tropical areas of land or sea? Or did it form actually over the equator? So tropical could be anywhere between the Tropic of Cancer and the Tropic of Capricorn. But equatorial means it has to be on the equator. Okay, that refers to the latitude at which the air mass formed. Okay, and we're going to have a picture here in a second. Yes, the next slide. And we'll have these symbols used to describe air masses on a map. But first, I want to say something about circulation patterns. The circulation patterns on the Earth are better understood now than they once were. And these circulation patterns influence the movement of those air masses. So, for instance, when air masses enter the United States, and by that I mean the lower 48 states, what we call the conterminous US, that is the states that share borders with one another. That excludes Alaska and Hawaii. The general movement of the circulation patterns are generally from west to east. So we call them westerlies. Remember, when you say west in terms of direction for air movement, wind movement, you're saying, which way do I face to feel that air moving against my face? So if I look to the west and I'm getting a blast of air in my face, that's a westerly. If I look to the east and I get a blast of air in my face, that's an easterly. Okay. So in the conterminous US, most of the movement is from west to east. Okay, so here we have land masses that can form, and we've given them these symbols to denote that this particular mass over Canada is continental. It forms over land, plus it comes from a polar region here. Whereas the one that forms over Greenland is actually, it's continental, but Greenland extends up into the Arctic. Excuse me. Okay. That's odd. Continental makes sense, but it's saying that this landmass is polar. Okay. So what we're looking for is what is its furthest reach? And apparently this landmass reaches all the way up to the polar regions, all the way up to the North Pole. Whereas this one only reaches into the Arctic region. Okay, so there's a difference there. This one in particular, which would form over the Arctic Sea, would be maritime. And it would be Arctic because it's coming from that region. This one would be maritime, but it's, let's see, maritime polar. Okay, this is maritime Arctic. This is maritime polar. Okay, I think I understand what's going on here. What was its origin? Where did this mass originate? Right? It might be here in this region right now, but where did it form? Well, it formed over water in the polar regions. And now it's down here in the northern Pacific. Okay. This one formed over the Arctic maritime area, but it's in this location now. So these abbreviations are meant to describe what was the origin of the landmass, not where is it now. This one down here over Mexico would be continental, obviously, and T for tropical. So it formed in the tropical region. Let's see. This one is maritime tropical. This one also is maritime tropical, and it's on a different ocean, Atlantic Ocean versus Pacific. This one is maritime, but it formed over polar regions, and it moved down into this northern Atlantic. Okay. So when we talk about an air mass, the thing about gases like atmosphere and things that are mixed in with it is the boundaries are not well defined. Rarely are they well defined. Not like we know when we describe the difference between a solid, a liquid, and a gas. A solid has its own fixed volume and fixed shape. A liquid has fixed volume, but not fixed shape, so it needs a vessel. A gas has doesn't have a fixed volume, and it doesn't have a fixed shape, right? So if it's not in a vessel, how do you define its boundaries? Well, the boundaries are defined relative to other air masses. And in that case, we call that a front. So when you have two air masses together that are against each other, they're going to have different characteristics, usually temperature and moisture content. And they form a front where they meet. Now, this meeting is not like it's not like a sheet of metal between them. There's mixing going on. So the boundary can be rather diffuse. Okay, so what's a cold front? The front also depends on movement. If you have a front, then the air masses are moving. So a cold front means that cold air mass is pushing through a air mass that is warmer than itself. And let's see. Yeah, I've got a slide for that in just a minute. There are symbols that we use to define a cold front. A warm front is the other way around. The warm air mass is moving, and it's forcing the colder air mass ahead of it. Right. So here we have an example of warm air here, air mass, and over here we have the cold air mass. And it says the cold air is moving. And generally speaking, when a cold air mass encounters a warm air mass, the cold air is denser, right? Obviously, because it's colder. When you get something cold, it tends to decrease its volume, and it gets denser, so it stays underneath the warm air, and it pushes against the warm air from underneath. So the front is going to be angled closer to the ground where the first contact is made, and then as the warm air rides up over the cold air mass, you get an increase in altitude of the front itself. So if you're standing on the ground, you may feel the cold front coming through, but there's more to it than that. The cold front actually extends up many thousands of feet. So as this warm air, which holds lots of moisture, it should have more moisture than the cold air, is forced up, what does it do? Just like against the mountains, it cools. And as it cools, it condenses. And you get very severe weather developing from cold fronts moving through. Whereas a warm front is illustrated in this one. Oh, and these symbols are indicative of the cloud types, these abbreviations. Let's see if I can remember what they mean. Cumulus, this is the Cumulus Clouds. And these are altocumulus, AC. When a warm front moves against a cold front, it tends to form a more gradual boundary. Because it is more difficult for lighter air to displace the heavier air. It just can't move it. So it forms a gradual boundary. And you still get precipitation. As the warm air rides up over the cold air, it condenses and falls, but severe weather rarely develops from a warm front. This would be cumulus, or let's see, CB. I can't remember what that one is. Stratocumulus, altocumulus, and cirrus. You get these various types of clouds that can form when a warm front moves through. Okay, meteorologists use standard symbology to indicate cold fronts, warm fronts, and in fact, other types of fronts. So on the weather map, so you would have an outline of your region with some information on it saying this is United States, may even have the states outlined. And then to show where the air masses are and how they are interacting with one another, you may have a cold front indicated by a line with the sharp teeth on it. That means a cold front. And the direction of those teeth means that's the way it's moving. It's moving the direction of that the teeth are pointing. Whereas a warm front will have these semicircles. And the way they point is the way the warm front is moving, pushing the cold air ahead of it. Now, things can get pretty complicated with weather. If you have, say, you have a warm front, right? A warm front like this, and it's moving that direction, but you've got a faster moving cold front behind it, right? This is warm, that's colder, but now you've got a cold front moving behind, and it's moving faster, which is typical. This is moving much faster. If it overtakes that warm front, then you get what you call an occluded front. These two fronts combine in some way. Now, they may not last for a long time, but this cold front overtakes this warm. It rides it. The cold front goes underneath the warm air mass, and then it eventually pushes that warm air mass up and meets the cold air before it. Now, this air doesn't have to be the same temperature as that air. It's colder than this air, but it doesn't have to be the same cold as that cold. Okay. But when those two fronts meet, you have an occluded front. Now, if you get these, a cold front moving in one direction and a warm front moving in the other direction, and they meet and they're stagnant, you get a stationary front. So you have warm air on one side, cold air on the other. So when it looks like this, let's see, when you have like that, like that, like that, and you have this and this and this. Now, which side is the cold air? The cold air is on the opposite side of the sharp peaks. So this is the cold side, and this is the warm side, because it would be showing movement that way. This would be showing movement that way. All right. But if it's not moving, it's stationary. You still have the cold and the warm air masses, but nobody's winning. It's not moving. So that's one of the types of information that you can gather from a weather map, is the air masses that are in a region and how are they behaving. Okay. So maybe we can say something about weather trends. Circulation around air masses can either be cyclonic or anticyclonic. Okay, definition time. Cyclonic movement means that the circulation of air is in the same direction as the movement of the Earth. So in the northern hemisphere, cyclonic circulation is counterclockwise. And that has to do with the Coriolis effect. Let's see, I don't think we've described the Coriolis effect yet. I think it comes later. Or did we? No, we did, I think. Yeah, we must have in chapter 19, the Coriolis effect. So the apparent movement of the air in an air mass would be counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It moves in the same direction as the Earth. So if the Earth is moving from west to east, then the air would move like that, or like that. Anticyclonic is air moves in the other direction. Okay, so when we define air masses, we also look at air pressure, which can be measured. And we described how that's done in a previous chapter in chemistry, I believe, where Torricelli built his barometer and measured air pressure with it. And what was noticed was that as the air pressure started to drop, you could expect bad weather. If the air pressure started to rise, then clearing weather would follow. Well, these pressures can be defined on a weather map in terms of, and you can measure them over large areas and then combine them on a map. And wherever the pressures are the same, you can draw a line connecting those pressures that are equal in value. Those lines are called isobars, bar referring to pressure. So everywhere on that line is exactly the same air pressure. So if we draw those on a map, those isobars, you'll get concentric rings. And for a low pressure, the lowest pressure is going to be here, and it'll get higher and higher out there. But for high pressure, this will be the highest pressure, and it'll get a lower this direction. So it can go lower and lower and lower and lower till you get to a low pressure. Well, when we define these pressures on a map, we find that the air circulates. We can measure wind direction also. The air circulates around a low pressure system in a cyclonic direction, and around a high pressure in an anticyclonic or clockwise fashion. Okay, so cyclonic is counterclockwise for our part of the world, and counterclockwise is cyclonic, and clockwise is anticyclonic. All right, now we have that firmly in mind. Low pressure systems, like I mentioned earlier, carry rising air currents, lots of clouds, and possible precipitation. So that's the bad weather that was mentioned earlier. Okay, high pressures generally indicate clearing skies, very few clouds, and fair weather. Now, there's some speculation as to why the air pressures are the way they are. And one theory explains it in terms of the moisture content of the air. If you have a lot of moisture in a low pressure system, then it decreases the density of the air. Whereas a high pressure system has low moisture, and the air molecules can come close together and form higher pressure. Now, I don't know if that's true. That's just one explanation that I've heard. Okay. So when we draw these maps, we can put lots of information on a weather map. And usually the weather map that's reported to the public by your local weatherman or meteorologist or whatever the case may be, will be a synoptic weather map. That is, it's a synopsis. It's like reading cliff notes for a novel. Instead of reading the novel, you read the notes and you get a synopsis of the plot. Well, this is a synopsis of all the weather information that you could get from measurements that are made over this, in this case, the lower 48, the conterminous United States. The weather map that the meteorologist sees is much more complicated. So they simplify it. They give you a synoptic version for public consumption, because all the public really wants to know is, what's the weather going to be like today? You know, do I need to carry an umbrella? Do I need to wear wear a heavy coat or whatever the case may be. So this gives you some basic information. It shows you cold front here, right? A warm front and a cold front. And in this case, they're both emanating from a low pressure system. So this cold air is moving that way, and it's pushing warm air ahead of it against this cold air. So it can become complex, very complex weather can be. And you have these low pressure systems and you have the highs. And typically the low pressures, if you're going to have a front, they're usually attached to a low pressure, whereas the highs usually stand alone. In this particular map, we also give an indication as to what type of precipitation you can expect. Right? These are showers along the coast. Thunderstorms have little lightning bolts. Let me see. Do I see any up there? Let's see. There's more showers. These little stars are snow. I don't see any lightning bolts. Right. Okay. Ice. Can we see any ice? No. This legend tells you all the possibilities, and we don't see all of them on this map. And then the fronts are defined, what we would typically expect here. Now, in this particular map, we're showing the noon positions of weather systems and precipitation. And the temperatures are listed as highs for that day. Now, when it says 28:15, that means 28 is the high for the day, and then 15 will be overnight. So it's day-night, is that what that slash means. Okay, so that's for public consumption. Here's another synoptic one. Gives you a different type of weather information. This one I downloaded from the National Oceanic and Atmospheric Administration, NOAA. And it's sub-bureaucracy called the National Weather Service. And this has several high centers of high, but one thing it doesn't show us is the isobars, right? Doesn't show us that. It just shows us the center of the highs and the center of the lows. Now, this one in particular, I see these dashed lines, and we didn't talk about those yet. I'm not sure what those are. Those could be stationaries. That could represent stationary fronts. But since this is a synoptic map, the symbolism isn't necessarily, or it could be occluded for all that matter, isn't necessarily what you would see on a bona fide complete weather map. Oh, I do see this is color-coded actually. This is a stationary front here between these two lows. And there you have a cold front, and there you have another cold front. And you see different types of precipitation that are indicated here. So it's a different legend. So you have to look for the legend and see what do these symbols mean. Some of them are standardized and some of them are not. All right. This would be a detailed weather map, and it gives a lot of information. I'll call your attention to first to indications of the low centers, the fronts, and now this one contains isobars, right? So if you follow this line around, they will all be at the same pressure. So this is the high pressure, and the next one over will be lower pressure, and then lower pressure, and then lower pressure, until you get over to an actual low pressure center. Other things it gets very busy in here. You'll notice these a collection of numbers here. These are called weather stations. And that's not, that's not a wooden structure with an anemometer on the top to measure the wind speed and a weather vane for the direction and a rain gauge and all that weather station. Now, those are the physical representations. Those are weather stations. But on a map, these weather stations contain information that is described in more detail in your lab exercise on weather. So study that document and it will show you how the weather station is constructed for a weather map. I'll just point out one here. You know that you've got the center of a weather station when you have a little circle and you got a flag off of it. That flag indicates the direction the wind is coming from, and those lines on that flag are interpreted for wind speed. So take a look at your weather lab exercise, and it will tell you what those flags mean and the numbers that surround each one of these stations. So the numbers that surround this station and the other symbols will indicate what type of weather has been recorded at that station. And that it typically occurs at 7 o'clock in the morning or 7 o'clock in the evening is the usual reporting time. Now, that's not hard and fast, but that's typically when they do it. Okay. Pressures. Some of these pressures are indicated with these numbers, right? 1003 or 1006 or 1019. The way that pressures are indicated, they're indicated in terms of millibars. A bar is a base unit for pressure, and a millibar is 1,000th of a bar. So when you see something like 1003, first thing you do is place the decimal point. The decimal point is left off simply because it would get too busy. So you put a decimal here to the left of the last symbol. So that's 100.3 millibars. Now let's see, on this particular map, I don't see any in the 900 range. Okay. So if you do, instead of, let's see. Hold on a second. Is that right? No, that's not right. No, that's not right. I told you wrong. I'm looking for okay, I can't use this map to tell you what I wanted to tell you. Let's see. I'm going to look ahead and see if there's another map coming. No. Okay, so we're going to have to look at the lab document. Gives you a better explanation. In fact, let's pause, and I'm going to get that. I'm going to pull that document up because it gives a better. Let me see. I'll tell you what. I'm going to stop this share. There we go. And I'm going to go find that lab. Excuse me. Here. I'll be with you in just a second. Okay, weather, here we go. Weather. Let's see, I'll use this one. Okay, so let me go back to, where is it? Here we go. Let me share you this document. So it'll look familiar to you when you look at the weather lab. So I'm going to share this document. There we go. So this is the weather maps lab, and here's what I mentioned earlier. The weather observations are typically reported at 7 a.m. and 7 p.m. Eastern Standard Time, at least for the United States. And let's see, let me go down here. Here we have some symbols. There are your fronts, symboled fronts. And here's your weather station. I'm going to have to shrink this a little bit. There we go. So your weather station is going to have lots of information around it. Remember that little circle with a flag on it, and these lines on that direction of the wind, and these flags mean the wind speed. Okay. Precipitation will occur in this position relative to that circle. Now, the content of the circle also indicates cloud cover. So we'll look at that in just a second. And then the time the precipitation began and end. Now, these are all indications of weather events, but every weather station may not have all the information here. Let's see. Okay, here it is. Barometric pressure at relative to sea level. Usually the initial 9 and 10 are omitted. So if you have a 147, then that means that you tack a 10 on the front. And it's 1014.7 millibars. And how do you know whether to put a 10 on the front or a 9 on the front? Right? So if it's 147, if you put a 9 on the front, and that would give you 914.7 millibars, right? Rather than this one. How do you know it's not that one? The reason is that this is outside the range of normal barometric pressures that have been measured over time. Right? It's too low. So you would typically you would know that you have to put a 10 there and not a 9. Okay, that's how we know which one to put, is because 914 millibars would be too low. You just don't get those low air pressures. Now, if we had something like, instead of 147, we had 847. You know, in this case, that you put a decimal there and a 9 there. Because if you put a 10 there, 1,084 millibars is too much. We don't get air pressures that high. Now, does this document tell us what those ranges are? Hold on a second. More symbols. A little overkill. These are good for determining symbols for precipitation, right? You see them right here, most of those. Let's see. This one, let me blow this one up. It prints okay. It's just when you look at it this way, it's not. No, let's make it bigger. And Here we go. I need to go a little bit more. There we go. This is a little easier to understand in a single slide. So here's your wind direction, and there's your wind speed with these lines on it. And these lines tell you, right? So you need this key to tell you how fast is fast. So with these two lines on there like that, the wind speed should be 21 to 25 miles per hour. The pressure, 138. So if we see 138, should we put a 9 there or a 10 there? Well, 913.8 is too low. It can't happen. So we put a 10. That's actually how many millibars this pressure is indicating. Okay, cloud cover, right? This circle in the middle says cloud cover. All right, we look down here, a solid filled in means 100% cloud cover, overcast. If it's, say, 75% cloud cover, we would have a slice of pie like this. Or if it's 50%, we'd have one like that. If it's perfectly clear, no clouds in the sky, then the circle will be clear. Okay, so let me go back down to a reasonable size here. All right. So here we have, let's see. We're going to read a map, figure 48.3, which is next page. And we're going to look for the weather stations. First one around Bismarck, North Dakota. Second one around Oklahoma City, Montgomery, Alabama, Houston, Texas, and New Orleans. And then you're going to gather from the weather stations on that map, what are the conditions? And write them in here. And remember, the temperatures on these maps in this country are in degrees Fahrenheit. Okay. Let's see. Figure 48.3. Okay, so we go down to 48.3. Is this it? Yep, 48.3. And you'll have to rotate that slide. Let's see, can I rotate it? Rotate clockwise. There we go. So when you look at this map, it's purposely simplified so that we don't get too bogged down. Where is Bismarck? Well, you might have to blow it up a little bit. Here we go. There's Bismarck right there. See? There's the weather station. And the weather station is, looks like it's got a line through the middle. So you go back to your key and you find out what does that mean. And then you look at it a little closer. Let's see. Let's blow it up some more. 200. There we go. Right, there's Bismarck. And it looks like it's got two lines on it that says it's 21 to 25 knots, miles per hour. Then you have, in this position is always the barometric pressure. So 220, if we put a 9 in front of that, that would be too low. So we have to put a 10 in front of it. So the barometric pressure is 1022.0 millibars. And then these others are temperatures. So you look at your representative weather station and say, which one of these temperatures is which, right? It's in this position. The high one here, the low one there, probably has to do with, well, let's go back down so we can, right. And let's rotate that thing back. Let's see, one more. There we go. You're also looking for, here's the pressure. Oh, 1 is the dew point. One is the temperature, one is the dew point. Usually the dew point is lower than the temperature. So the lower one below. And if we look up here, let's see. Oh, you can use this one as an example, right? So the city A has the air temperature is first. And if you look on the map, you'll see that it's, well, let's see, we need to go back up to our weather station and blow it up again. Here we go. There we go. So this is the temperature, the higher one, and then move down here, that's the dew point. So you have those two temperatures. One is the temperature, one's the dew point. And plot those. Let's see, what did we see before? We saw one with a line through it like this. So that's 90% cloud cover or broken clouds. Okay, so let's go back and see if there's anything else here that I want to point out before we move on with our PowerPoint slides. There's one weather map. Here's another one that you'll need to use for another part of the to answer the questions. And while we're here, I'll just point out the fact that up to this page, page 13, all of those are required. Anything past page 13 is bonus. So if you answer these questions, if you do the work that's required, this one, right here, you draw out this map and it's worth lots of points. Then you get bonus credit for anything past that point. Okay, so let's unshare this one and go back to our slideshow. And let's see, where was I? Getting close, getting warm. Here we go. We were at this one. Okay. So this would be a weatherman's or a meteorologist's detailed map. You know what I'm thinking is that these values, this 1006, that is barometric pressure. But in this case, they're leaving off the last decimal point. It's just doesn't appear to be standard. Yeah, it doesn't appear to be standard. In fact, these lines may not be. These lines might be, I don't know what they are. They may not be isobars. They could be isotemps, right? Same temperature. Okay, let's move on. Okay, there are certain types of conditions that are believed to have an impact over wide areas of formation of weather systems. One of those is called El Nino, and El Nino means the little boy child, presumably based upon the Christ child, El Nino. And because it usually starts around Christmas time, where you get an accumulation of warm water in the eastern Pacific, the central and eastern Pacific. During a normal year, the warm water accumulates over close to Japan, Indonesia, Southeast Asia. That's a normal year. And that warm water will generate air masses with that characteristic. But if that warm water somehow moves or becomes predominant in this part of the ocean, it produces air masses with that characteristic closer to our continent and has an impact on North American weather. Okay, let's see, did I miss anything here? No, okay. During a normal year, the waters off South America are normally cold and nutrient rich. That's because of ocean circulations. In other words, in the tropics, the sun beats down at pretty much a constant rate all year round, and it warms the water around close to the equator. Well, when it warms the water, it expands, becomes less dense, and rises. Well, when the water masses, like air masses, when water masses rise, something's got to take their place. So colder water moves in from around, and that typically means from the Arctic region. So that cold water moves in to replace the warm water, and the cold water is moving across the ocean floor, picking up nutrients as it goes. And when it gets to the off the coast of South America in the Pacific, then it starts to rise because the warm water is being heated and moved out. So you get these upwellings of cold, nutrient-rich water, and you get the ecosystem starts to bloom. In other words, the nutrients cause the microflora to have a population explosion. Smaller fish and crustaceans eat those plants, those single-cell plants, and then the larger fish eat them, and then it cascades until you get to the point where you have an explosion of fish. And that's why the fishing grounds off South America are typically very rich. And that's why there are lots of birds there too, because they go out and fish for them, and then they nest on the coast of, say, Chile. And when they do, they poop a lot, right? And there are regions along the coast of Chile where the guano, the bird poop, is a couple of 100 meters thick. They've been doing it for centuries. Okay, so every 3 to 5 years or so, the winds across the Pacific shift. They change directions, and they blow this warm water, which is typically nutrient poor, from the Western Pacific to the Eastern Pacific, and that shuts down the movement of cold, nutrient-rich water from the depths, from the Arctic region as it moves north, and it shuts that down. And then you have the ecosystem that supported all those fish crashes. And it's believed that it doesn't just affect the local weather. It's believed that larger regions of the globe are influenced by this shift of warm water from the Western Pacific to the Eastern Pacific. And that's largely due to the fact that we actually see these things happening, and there's a correlation. We're not sure if it's a cause and effect, but there is a correlation between movement of that warm water to the Eastern Pacific and adverse weather that we're experiencing globally. Okay. On a local level, you can get what we call storms. Those are atmospheric disturbances that can develop within a single air mass, or can develop where one air mass collides with another one along these frontal boundaries. We generally divide them into two types: local storms, which do develop typically where air masses collide. Although you can get some pretty severe weather in the lower portions of the United States, where you have in the summer, where you have during the day, heat builds up. It just builds up and builds up. And evaporation of moisture from the land surface just builds up the moisture in the air. And it, at some point, the buildup in the heat of the air moves, continues to rise, and as it rises, it starts to condense into clouds. And you get what we call convection showers, because the convection currents cause this moist air to rise, and the higher it rises, the colder it gets, and eventually it reaches a point where the precipitation comes out of it. These convection showers don't need fronts. In fact, I lived in Louisiana for 13 years, and during the summer, you'd get these convection showers practically every day in the afternoon, about 4 or 5 o'clock. And actually they were welcome, because you get 95 degrees and 95% humidity, and it was just unbearable. So when the convection showers came in the late afternoon, the temperature would drop precipitously, and everything would be more comfortable into the evening. Well, that's a local storm. Tropical storms form in the tropics, and they typically don't require fronts. Certain conditions have to be active, and they're still studying those tropical storms, which can develop into hurricanes. Local storms, right? We'll talk about the tropical storms again in a minute. Local storms can take the form of simply rainstorms, just lots of heavy rain. They can be thunderstorms that have lightning in them, which is the source of the thunder sound. They can even be ice storms. You can have storms in the winter that form from these systems. Snowstorms. You can have some, if the conditions are right, you can develop tornadoes. And that is a very severe local storm. Usually when the downpour of rain exceeds 1 to 3 inches per hour, or reaches 1 to 3 inches per hour, we call that a rainstorm. If the rainstorm is accompanied with lightning and thunder, and sometimes hail, then we have a thunderstorm, right? So these are, they're not, at best, they're semi-quantitative. These are qualitative descriptions by and large. So one man's rainstorm would be another man's thunderstorm. That's what I'm trying to say. Let's see, that's not, that one's supposed to be animated. So let me move that out of the way so we can see the words. Here we go. I'll bring it back in a second. Here we go. Lightning. When does lightning form? Lightning is simply the transfer of charge from one location to another. So and it's a static electricity phenomenon. So certain conditions develop in, usually in clouds, where you get a separation of charges. And this is largely due to the movement of air. When you get movement, you can get separation of charges. And if you get a large enough separation of charges where you develop a huge potential difference between these two positive and negative charges, then certain conditions will cause them to equalize. In other words, the charges will be transferred, usually from negative to positive, because the charges are being transferred by electrons And when that happens, you get a lightning strike. And all that's happening is the unequal distribution of electric charge is now being equalized by the discharge of electricity. And the voltages are massive. They can be in the millions of volts difference between the positive and the negative side. Okay. Lightning can occur based primarily upon where does it start and where does it end. Okay. It can be entirely within the cloud, right? Called intra-cloud. So one region in a cloud can be heavily positive, another heavily negative, and you can get a discharge in the cloud. Or you can have two clouds at different potentials, and the lightning strike can transfer from one cloud to another, cloud to cloud. Or if there's a potential difference between the cloud and the ground, you can get a lightning strike between the cloud and the ground. Under special conditions, you can get a discharge from cloud into just an air mass. Those are kind of rare, actually. But there has to be this potential difference, a voltage difference between an accumulation of positive and negative charges in order for it to occur. Under any of these circumstances, that is prerequisite. Or you can get a transfer, you can get a strike between air masses. And that's what I'm showing here with this picture. These typically occur at very high altitude. These are called sprites. This is an interesting picture, but they were first noticed by astronauts who could see these discharges at very high altitudes from their vantage point in low Earth orbit. And then once we knew they were there, we started looking for them from the ground or from airplanes. Okay, so those are the different types of lightning strikes that can occur based on origin and destination. Lightning is dangerous. Right? If you get hit by a lightning strike, there's a very high voltage and current. In electricity, we speak of, and this was in first semester, in electricity, we speak of voltage as a difference in potential. In other words, what's the driving force behind the movement of charge? And we also get current. How much charge is being transferred from one location to another over a given period of time? So a large amount of charge transferred in a short period of time is a very high current. And you know what they say about electrocutions, or executions for that matter, in the electric chair, is it's not the voltage necessarily that kills you, it's the current, how much charge is transferred. So if you have a condemned prisoner that's strapped to the chair, they transfer at high voltage, of course, but large current goes through the body. And basically what it does is it stops the heart, if you're lucky. So if you get hit by a lightning strike, the chances are that you're going to be killed. Not always. There are some people that are lucky, so to speak, of being hit and not killed. It's not understood exactly why this happens. So I won't even speculate at the moment. But approximately 200 people are killed each year by lightning. And I assume that's worldwide. So not too many people die from lightning strikes, but it does happen. So let's talk about lightning safety. What do you do when there's lightning in the area, right? Say if any of you watching this video are golfers, then you know that when you're out on the golf course, there's lots of open space, and they're usually trees. In this part of the country, there would be trees. So what do? Well, if it's just raining, you know, some hardcore golfers like I used to be, would just play right on through the rain. But if you hear lightning, if you hear thunder, or you see a lightning strike in the distance, you better run for cover. Stay indoors. Stay away from open windows. Stay away from fireplaces, because lightning can travel through air, even down a fireplace for that matter, or through an open window. And stay away from electrical conductors, right? Don't wash your dishes in a lightning storm. Don't take a bath in a lightning storm. Okay. I went to school with a girl, high school. And her family had a cabin up in the country. This was in Georgia. So up in the mountains, they had a cabin, and she went up there to spend the weekend by herself. And but she wanted to talk to her friends on the phone. And this was in the days when we didn't have cell phones. You had landlines. So she was taking a bath and talking on the phone to her friends in a thunderstorm. Lightning struck the telephone line outside the house. It went through the wire, through the phone line, through her ear, into the water, into the ground, and she was dead. During a lightning storm, it's probably a good idea that you don't use your computer or your radio or your TV or even turn on a lamp. And it's a good idea, if you can, to fit all your appliances with surge protectors. So this, not only does it protect your equipment against electrical surges that may come dashing through your power lines, it will also help protect you from potential electrocution if you happen to be touching one of these devices. Now, there are limits to surge protectors, right? They have ratings, right? How many amps can they handle? Milliamps usually. So it may not be complete protection, but it may subdue the amount of current transferred enough to where it doesn't kill you. Okay, enough of that. If you're caught outside, find shelter indoors if possible. If you're away from buildings, you can't find cover, then try to become the lowest thing in your area, on the ground, in a ditch, in a ravine. Lightning will tend to strike the highest object in its area that is at the difference in potential that attracts the lightning in the first place. So if there are trees around, you don't necessarily want to get under a tree, but you do want to get in a ditch lower than the tree. So if lightning strikes, it will tend to strike the tree and go into the ground. Okay, that being said, let's move on and say, what is thunder? Well, like I said, thunder is a consequence of a lightning strike. And in order to have thunder, which is sound, you have to impart energy to the air to generate that sound. And the way we impart energy to the air is through traveling charge through the air. And it travels at high voltage and heats the air as it moves, as the charged particles move through the air on their toward their destination. There's such high voltage and such rapid movement, they heat the air. They make it hot. And when it gets hot, it expands and causes a pressure wave generated by that passage of that lightning strike. And that pressure wave is what you hear in the distance as thunder. If the lightning strikes so close that you can't tell the difference between the light you see and the sound you hear, then it's really close, within the length of a football field, probably. And it sounds like a single thunderclap. If there's a difference between you see the lightning and you can count so many seconds between the lightning and when you hear it, then it's very far in the distance, and you tend to hear not a single clap, but a rumble, a rumbling sound. And the rule of thumb is, if the lightning is, if you want to know how far away the lightning is, well, you need to know something about how fast does sound travel in air. It generally travels about 1,000 feet for every second. So if you count 2 seconds from the light to the thunder, then it's a couple of thousand feet away. Or if you count 5 seconds, it's about a mile. Okay. And that's based on the fact that the light travels at about 300,000 kilometers per second. Right, very fast. It's virtually instantaneous. But the sound travels at about 1/5 of a mile per second, 1,000 feet per second, or 1/3 of a kilometer per second. So if you count the time, then you can estimate how far away it is. And if there are several thunderclaps and they're coming from the same system, and the time that you count from one measurement to the next is constantly decreasing, then you know it's moving toward you. And that gives you some advance warning, of course. Okay, so this is just an exercise in how far away is it? And I'm not going to dwell on this. It's just distance equals velocity times time, right? That's what we learned in the first chapters of the first semester of physical science, in Physical Science 101. Distance equals velocity times time. It works for sound as well as it works for any object, like a car or whatever we were using as our example in that course. So if you know how fast sound travels and how long it takes to get there, then you just multiply those two together and you find out how far away it is. Okay, we mentioned other types of storms, ice storms. This type of storm occurs when you have rain coming from a cloud, a system, but the surface of the earth is at or below freezing. So when the rain hits the surface, it instantly freezes. That's an ice storm. The water freezes, the precipitation, the rain freezes on contact, and it builds up a layer of ice. That can be very dangerous, especially for travelers. But the weight of this ice that accumulates on various things, it can snap tree branches or knock trees down, or it can accumulate on power lines and cut power. It can cause lots of damage. Snowstorms, on the other hand, just simply mean that over a given period of time, there's going to be a large accumulation of snow. So on this day that I'm making this presentation, we had an accumulation, and this is March 12th. We had an accumulation of snow in the order of 6 to 8 inches outside. That may not qualify as a snowstorm, but there was quite a bit of accumulation of snow over a period of a couple of hours. And this occurred at a time of year when you wouldn't normally expect snowstorms, right? In March, I mean, we're moving into spring, right? Just a few days away from the actual vernal equinox. Okay, so when a snowstorm is accompanied with high winds and low temperatures, we classify that as a blizzard. And the high winds are key to that. You have a snowstorm plus high winds is a blizzard. The danger of blizzards is the snow is very light. I mean, even if it's wet snow, before it hits the ground, those high winds can drive it ahead and up against objects can build up large piles, snow drifts. And those snow drifts can cause a lot of damage too. They can deny you access to your car or your building. They can accumulate more snow on one side of your roof than the other and collapse roofs. And in addition, with the high winds, you get the effect of wind chill. High winds means that the temperature that you feel is lower than the stationary air temperature and can cause hypothermia much faster. So there's a hazard there if you're caught out in a blizzard. Okay, let's go back to tornadoes. Tornadoes are a localized violent storm with high winds in a cyclonic direction. They're counterclockwise always. So they originate from low pressure systems. These are the most violent storms that actually originate on land. Now, hurricanes are violent storms, but they originate over oceans. And sometimes they make landfall. And the dynamics are much different for hurricanes than they are for tornadoes, even though their circulations are both cyclonic. Tornadoes are very localized. In other words, those high winds up to 200 or 300 miles per hour are circulating in a small area, relatively speaking. Some of them can be 100 feet across. Some of them can be a mile across. Those are really big ones. And they concentrate a lot of energy in a small area. That's what makes them really dangerous. So they can uproot trees, they can destroy power lines, they can collapse buildings, they can pick up animals, trucks, people, and sling them around. And that's where they really become dangerous, because if they destroy a building and pick that building up and mix it up like that, it's not just the wind that hits you when that tornado, if you're unlucky enough to encounter a tornado, when it hits you, there could be debris in that tornado that strikes you with more concentrated force in a small area than the winds would. Okay, where do they occur? Tornadoes typically occur most often in the United States and Australia. That must mean that the atmospheric conditions are just right for forming tornadoes over those the US or Australia, those two land masses. That's not to say that tornadoes don't occur elsewhere. They're just not as common. In fact, the largest number of tornadoes on the planet in any one year occur in the United States. And they typically occur in this zone between, let's see. Let me see if I got a map already drawn. I do have a video coming up, though. So if we look at the United States as, let's see, Canada, and then we have Maine, and then we come down here, and there's Florida, and we come over here, and there's the Gulf of Mexico. And then we have the Pacific coast. Like that. Okay, the Rocky Mountains are here. The Appalachian Mountains are here. And that is Tornado Alley. That's where most of the tornadoes occur in the United States, in that central region between the two mountain ranges. So there must be something special about this region that causes tornadoes to occur more commonly there than anywhere else. And they tend to occur April, May, June, okay, are the peak times. So what do we have? What are the conditions? Well, we've got the Gulf of Mexico, blowing winds up off the water here. And this is warm, moist air masses coming off of the Gulf of Mexico. And what's coming down from this, and these mountains tend to funnel that air, those air masses, tend to funnel the air masses here and bring them up here. So what you get is cold, dry air coming down from Canada meets warm, moist air coming up from the Gulf. And the large difference in temperature and moisture content is a major contributing factor to the development of thunderstorms and tornadoes. So, with that being said, atmospheric conditions that lead to tornado formation. Number one, instability. Stable air is air that is not, it doesn't need to go anywhere. It doesn't need to make much change to reach an equilibrium state. Unstable air, however, does try to find a low energy position. And when it does, it has to release energy to get there. So if it's unstable, then you tend to get storms. So this warm, moist air moving up from the south, and cooler, dry air moving in from the north meet, and when they meet, they produce what we term as wind shear. It's a change in wind direction, right? The winds are blowing this way, the winds are blowing that way, and you get very, very large differences between wind velocities from one direction and the other direction. So large wind shear is required. And that's a difference also in height, right? So a change in wind speed with height is wind shear. We often hear of wind shear in terms of when we hear of an airplane accident. They say, oh, that airplane crashed because of severe wind shear, a difference in wind speed with altitude. And typically what you see is a microburst toward the ground. And if that happens, then it doesn't matter how fast the plane is moving together to gain lift. If the wind that it's moving in is going like this, it's going with it. So it crashes. So wind shear is rapid change in wind speed or direction relative to its height. These strong updrafts that can occur are an indication or a result of wind shear. The wind shear also promotes rotation. And the rotation is always cyclonic, right? This way. But in the video that's coming up, I think we're going to get a better idea. The producer of this video explains the formation of a tornado much better than I could. And they have graphics also that helps. So let's go to the next slide and look at this video.
What causes a tornado? The swirling, funnel-shaped winds of a tornado are easily recognizable, and they can be very dangerous. But what causes these unique and violent weather phenomena? Tornadoes usually begin with a thunderstorm, but not just any thunderstorm, a specific kind of rotating thunderstorm called a supercell. They can bring damaging hail, strong winds, lightning, and flash floods. Supercells form when air becomes very unstable and wind speed and direction are different at different altitudes. This condition is called wind shear. Wind shear is common in the formation of most thunderstorms. When wind at ground level is blowing in one direction and wind higher up in the atmosphere blows in a different direction, it can cause a horizontal tube of air to form. In a thunderstorm, warm air rises up within the storm. This is called an updraft. An updraft can turn a horizontal rotating tube of air into a vertical one. When this happens, the whole storm begins rotating, creating a supercell. Some supercells form a funnel cloud. And if that funnel cloud extends to the ground, it's called a tornado. Tornadoes can produce winds up to 300 miles per hour at the surface, making them dangerous to people and property. As a tornado moves along the ground, its strong winds begin to pick up debris too. In fact, flying debris is usually what causes the most damage in a storm. Thankfully, meteorologists are keeping an eye on your local weather. They will try to give you a heads up if a tornado is likely to form in your area. They combine wind and temperature readings from the ground with information from satellites to determine if your local weather has the right conditions for a tornado. For example, NOAA's Goes East satellite captured this video of an isolated supercell storm in Texas. The different colors represent different cloud top temperatures in the storm. Colder temperatures represent higher cloud tops, which often means stronger storms. So, if you see a tornado watch or warning in your area, look for updates and get to safety as soon as possible. And know that NOAA's GOES-R series satellites will still be keeping a close eye on things from orbit. Find out more about extreme weather at NOAA SciJinx.
Okay. Let's see. I'm catching up here. All right. The narrator mentioned tornado watch, tornado warning. Those are two different things. The tornado watch is issued when the Weather Service determines that atmospheric conditions are favorable for the formation of a tornado. Nobody has seen one yet, but the conditions are right. A tornado warning is issued when a tornado has actually been sighted visually or has been indicated by radar. Remember, I think we talked about Doppler radar in chapter 19. A Doppler radar can show you circulation within that supercell and show you that that there is a tornado there. Even if you don't see it visually, the radar says it is there. That's when you get a tornado warning. And certain parts of the country, especially those in areas that are prone, like the Panhandle of Texas, Oklahoma, let's see, even parts of Arkansas and Missouri, and up through the middle part of the country, very often you will have warning sirens that are placed strategically throughout a region, and they will sound if a tornado or a severe storm has been spotted. So you don't necessarily have to pick it up on your cell phone. Okay, so this is what a tornado might look like, right? You notice it's got the funnel shape. It's thicker at the top and thinner at the bottom. And down here at the bottom, you can see it's developing a debris cloud. So it's picking up debris, and you're seeing that the circulation here is not just in the part that you can see. The air is circulating in a wider size than the visible part of the tornado. Okay, the severity of a tornado is rated in one way of rating it is with this F scale, the Fujita tornado scale. It was developed at the University of Chicago in 1971 by this researcher. And the F scale goes from a 0 to a 5. And the wind speeds that are required to produce these effects that are given. So if the wind speed is between 40 and 72, you may get some damage, some broken trees. It's relatively mild as tornadoes go. But as you increase the speed through these various ranges, you observe these types of damage to vegetation, to houses, to property. And you can go up into the 300-mile-per-hour range. In this case, there is almost total destruction in the line of the hurricane. Now, I've seen what a hurricane can do. I never lived in this hurricane alley, but when I grew up in Atlanta, Georgia. And one morning I was on my way to work. I was going to college at the time, but I was working also. And I got up one morning and I heard this sound. It sounded like a freight train. Well, I didn't think anything of it because where I was living in my parents' house, we were within a half a mile of Inman railroad yards. It was a train switching yard. Lots of tracks, lots of trains coming and going. So something that sounded like a train was nothing to think about. When I got to work, I saw the news broadcast that Atlanta had been hit by a tornado. And it had traveled probably within 2 miles of my house. Fortunately, it didn't come near us. But after work and school, actually the next day, I went out and drove around to look at the damage. And I saw where it started. And then I followed the roads. I knew how the roads went, so I followed the roads. And everywhere that tornado went, total destruction. Nothing left standing. I found an apartment complex where the tornado had gone through. All the trees gone. The right through the middle of the complex, all the buildings completely collapsed. And a lot of the material was scattered elsewhere. So these things are very dangerous. Fortunately, by the time it came in, a lot of people were not in their homes. They had gone to other parts of the city for work or recreation or school. So the loss of life was relatively small. Oh, here's a picture of the tornado path. And you can see from this picture that you have these structures over here, relatively little damage. Well, there's one over here that lost its roof. I don't know what that could have been. It might have been a greenhouse. I don't know. Anyway, everything in here is totally destroyed. And then houses right next door, totally untouched. That's the way tornadoes work. Okay. Here's a map with showing the average number of tornadoes per year. And the region, the highest number of tornadoes per year is right here in the middle of Oklahoma. Right? You've gone far enough inland where this warm, moist air is meeting this cold, dry air and coming down, and there you have it. Supercells form tornadoes. Now, that doesn't mean that's the only place it happens, but it's the largest area that produces that result. Okay.
Hollywood loves a good tornado. Like most things Hollywood, it's all a little dramatic. But flying cows aside, there is something accurate about the setting.
Meaning we're not in Kansas anymore.
You're not, but the tornado started there, which makes sense. Tornadoes are far more common in the US than anywhere else. For perspective, all of Europe records around 300 tornadoes per year, whereas the US records well over 1,000. If we move in a bit closer, you'll see that most of the world's tornadoes are happening here, in an area called Tornado Alley, a place that's absolutely perfect for twisters. Tornado Alley doesn't have any official boundaries, but it's typically considered this area that extends from northern Texas through Oklahoma, Kansas, Nebraska, Colorado, and South Dakota. Some people extend it even further east. While most states in the US have recorded at least one tornado, this area is really a hotbed, and the main reason for that is geography.
The central part of the US is unique in the fact that there's this really large, warm area of water just to the south, and the wide, high range of mountains that extend a long way from north to south.
Harold Brooks is the senior research scientist at the National Severe Storms Laboratory. He used to chase tornadoes. Now he studies them from Norman, Oklahoma, in the heart of Tornado Alley. A tornado requires a couple special ingredients that Tornado Alley is full of. First, we need a thunderstorm, which we're going to make right now. Sort of.
To make a thunderstorm, the things we need are warm, moist air at low levels, cold, dry air above that, and some mechanism to lift that warm, moist air up.
In Tornado Alley, lots of warm, moist air flows into the plains from the Gulf of Mexico, and cool, dry air flows from over the Rocky Mountains here in the west. Eventually, a change in temperature or pressure will arrive and lift that warm air up into the cool air, forming an updraft. Once these two meet, the moisture from the warm air begins to condense, forming clouds, and a thunderstorm begins. Under normal conditions, rain would fall from these clouds and cool the warm air, breaking the storm. But in Tornado Alley, there's a strong air current flowing from west to east known as the jet stream. This, paired with the cool mountain air, blows the rain away, keeping the air on the updraft warm and wet, which allows the storm to intensify and brings us to step 2, getting the storm to rotate. To make that happen, we need winds moving at different speeds and directions. As you can see, Tornado Alley has it in abundance. The air coming from the Gulf moves slowly into the plains. Meanwhile, the jet stream from the mountains provides a steady stream of high, fast-moving air flowing east. Because the jet stream is flowing faster and in a different direction, it causes the Gulf wind below to rotate, like a spinning football. When the spinning air gets pulled into the updraft, it's tilted, but continues to spin, causing the entire updraft to rotate. Storms like this are known as supercells, and they create prime conditions for tornadoes. They're rare, but most commonly occur in, you guessed it, Tornado Alley. As the supercell grows, the spiraling updraft begins to stretch towards the ground and forcefully pulls air into the cyclone. Air rushes in from the sides, and a spinning dust cloud forms below, which brings us to the final stage, getting the vertically spinning air to the ground.
Stage 3 is the friction in the teacup.
It's like using a spoon to swirl tea leaves at the bottom of a cup. The tea leaves rush into the center and are pulled up through the middle of the tea cyclone. In a real tornado, everything around the cyclone is sucked up. Air, dirt, debris, cows. As more and more air is pulled in tightly, pressure builds, and the faster and longer that tornado gets, it stretches closer to the ground until it eventually meets with that dust cloud. And then it touches down.
We see most tornadoes in the central part of the US because of the ingredients that are necessary for a tornado come together there more often than any other place.
The United States isn't the only place that gets tornadoes. Southeastern Brazil and northeastern Argentina have some of the same ingredients Tornado Alley does. Cool mountain air coming over the Andes and warm, moist air coming from the Amazon. But even still, the frequency of tornadoes is scores behind the US. While the right conditions come together, sometimes the geography isn't exactly right.
In South America, the Andes aren't as wide as the Rockies, and the Amazon isn't as good of a moisture source as the Gulf of Mexico is because it's land. It's sort of a Goldilocks problem.
and a delicate recipe. Most people will go their entire lives without ever seeing a tornado, and some would consider that lucky. Others actively seek them out, and those that do start in Tornado Alley, where the geography is just right.
Okay, so I can't explain it any better than that. Okay, how about tropical storms? These form over warm ocean water, but that's not the only ingredient that you need. These are very large weather disturbances that, like I said, form over tropical oceanic waters. And for the tropical storms that come into contact with North America, Mexico, and the United States in particular, their origin is just off the west coast of Africa. You get hot, dry winds blowing across off the desert, the Sahara Desert, into the ocean, and the hot, dry picks up lots of moisture as it as it moves across the ocean. And naturally you get instability. That's also a prerequisite for tropical storms. Now, if the tropical storm builds up wind speeds in this cyclonic direction, and it's always cyclonic, counterclockwise, and it reaches 74 miles per hour or greater, then we classify that as a hurricane. Hurricanes typically cover not just several yards wide like a tornado, but hundreds of miles wide. They're huge by comparison to a tornado. And the winds can be substantial also. I mean, all they need is 74 miles an hour and you have a hurricane, but they can go higher than that, much higher. There have been hurricanes recorded over 200 miles per hour wind speeds, sustained wind speeds. So, tropical storms that reach that wind speed are called hurricanes in the Atlantic. In the Western Pacific, they're called typhoons. In the Indian Ocean, they call them cyclones. And then I'd never heard this one before. In the region near Australia, they call them willy-nillies. Willy-willies. Willy-willies. Okay. So when do these storms typically occur? Well, they tend to peak in late summer, early fall. So that tells me one thing, that the conditions are much different for hurricanes than they are for tornadoes, because tornadoes and the thunderstorms that give rise to them, the supercells, form much earlier in the year. So my guess is that you have to build up a lot of heat in these ocean waters, and in order to get the instability required to form that circulating storm, the tropical storm. Not all hurricanes strike land. Some of them stay in the ocean, but they generally move in the northern hemisphere from east to west. And once they reach higher latitudes, then you get the jet stream imparting some change in direction. That's why you see these curves here, right? These tropical storms and hurricanes move in toward the Gulf, and sometimes they go all the way in and strike land there, but sometimes the air currents direct them back out into the ocean. And in order for a hurricane to sustain its energy, it has to be constantly extracting energy from warm ocean water. That's required. So once it moves into colder waters, then it starts to die. Or when it moves over land, it no longer has access to those warm waters, and then it starts to die. It starts to weaken. Okay, tropical oceans give rise to hurricanes. Enormous masses of moist air are required. So as the air is heated, a low pressure cell develops in the center of the storm, and you start to get cyclonic circulation as the air moves in from the outside into the center, as you would see in the formation of the tornadoes. Similar activities, only on a larger scale, and the storm starts to rotate, primarily due to the Coriolis effect. And as the warm, moist air rises, it cools. And when it condenses, it gives off massive amounts of heat. This is called latent heat. So the moisture is a gas, and when it condenses into a liquid, it has to give up that heat, right? There's more energy in the gaseous state than there is in the liquid state, and when it condenses, it gives up all that heat. And that heat is used to drive the tropical storm, the hurricane. And that's what energizes the hurricane. Okay, here's a satellite image of let's see, which one is this? Hurricane Jean in 2004. It has already struck the Bahamas, it looks like, and looks like it's on its way to Florida. Let's see, what's this one? Excuse me, let's back up. This one is in 2004. Oh, this is Jean also, right? This is the day after. But in this case, this is a radar composite that's showing the wind speeds and precipitation. So you notice that once a hurricane forms, you typically get this well-defined central region where the winds are perfectly calm, called the eye of the storm. And among other reasons, that's largely due to the centrifugal motion. So as the hurricane spins, right, what do you feel? You feel a centrifugal force that pushes things out. And you get, in this cross section here, in this lower diagram, here's the eye, and the vertical height is here in thousands of feet. And I'm thinking this is maybe a composite of rainfall or moisture measurement. So in the eye, things are perfectly calm. Now, I've never lived through a direct hit from a hurricane, but I have relatives who have, who lived in Florida. And when the hurricane came through, the winds are moving from the northwest, like you would see here. They're circulating that direction. And then the eye comes over and things just get perfectly calm. And then however long it takes for the eye to move over, and then the other side of the hurricane comes in with winds moving the other direction from the south in this case. So it's an odd feeling. So just if you're in a hurricane and it gets calm all of a sudden, it ain't over yet. Okay. So what about the amount of energy that's actually released in a hurricane? It depends on the size, how fast the winds are moving, the intensity, and these factors combined tell us that hurricanes are the most energetic storms on the planet. Now, Earth is not the only planet that has these cyclonic circulations, right? There's a huge one on Jupiter, the red storm, red spot. It's been going on for 100 years or more. So these atmospheric disturbances are not unique to the Earth. So how do you estimate the amount of energy that's released in a hurricane? Well, nobody really agrees, or there are differences of opinion. Different methods have been used. One method simply says how much rain is produced. And if that much rain is produced, we know that as the water condensed, it had to give up a certain amount of energy. So we calculate the latent heat that's given up from the amount of rain that's produced. And one estimate, right, is in the neighborhood of 10 to the 11th kilowatt hours, right? You know, electricity that comes into your house is measured in kilowatt hours. That's a measure of energy. And for a hurricane to release 10 to the 11th kilowatt hours of energy is huge. I mean, it's unfathomable. Another way to measure it is what's the kinetic energy of the winds? We know how fast the winds are moving. Based on the size of the hurricane, we can estimate how much wind is actually moving at that speed. And we can estimate the kinetic energy of the gas as it moves in that circulation and that speed. And that estimate is 10 to the 9th kilowatt hours, right? So it's a couple of order of magnitude less. So you can get wide variations in the estimate of the power that's generated during a hurricane. This smaller value, 10 to the 9th kilowatt hours, that's about half of the electrical energy generating capacity for the entire planet, right? In just one hurricane, right? And if we consider the higher value, that's several times greater than the generating capacity for the whole Earth. So that just gives you an idea that hurricanes are big, big, big energy generators. Okay, now we've got these high winds, but the fact of the matter is most of the deaths and the property damage that occurs from a hurricane is from water damage. So most of the deaths are from drownings. Most of the property damage is from flooding. And the flooding occurs described in terms of what we call storm surge. All right, I've got an illustration for that in a second, I think. Yes, storm surge. Storm surge, by definition, is a great pile of water that comes on shore because of the high winds. Remember, when winds are blowing across the surface of the water, there's friction between the wind and the water. And that friction tends to push water in the direction of the wind. And it piles up, especially as you get close to the shore, right? It can't move across more water. It moves onto land. And as it moves up onto land, it piles up. And the level of water that reaches land is many feet higher than a normal tidal surge when the storm makes landfall. Now, that's primarily caused by the wind, but you also get some effect from low pressure. So think about it this way. If the pressure in a hurricane is very low, and it is, the lowest measured air pressures occur inside a hurricane that we know of. My guess is that you've got low pressures inside tornadoes too, but we're talking about hurricanes right now. So this low pressure above the surface of the water is what? It's like a vacuum. It sucks the water up into it like this due to that low pressure. So the combination of pushing the water ahead of the winds and the low pressure causes the water to build up and pile up into a dome when it comes on land. And here's an illustration, right? If this is mean sea level right here, a normal tide might be a couple of feet higher than normal sea level, right? It could range, right? But a storm surge may add 15 or 20 feet of extra height to the water as it comes on land. And that causes lots of damage. So my advice to you is, if you're in an area that's prone to hurricanes, primarily coastal regions, then if there's a tornado headed, a hurricane headed your way, or even a tropical storm, and it looks like it's going to hit your region, I would go inland a long way. And generally speaking, if I go inland from the source where the hurricane's going to strike, I would move north and west, because when a hurricane hits landfall, it may go inland north for a while, but eventually it's going to turn east. So go north, west, and elevation if you want to stay safe. Then there's a situation where people are, coastal regions are not uniformly flat. They may be higher elevations near the coast, actually, and then inland, you may dip down some and go out. So if your roads pass through those areas of depressed land forms, then when this surge comes in, it can dump a lot of water into those low regions and cover the roads, and you're trapped. So get out sooner than better. Unless you just really, really, really want to live on the coast and you're willing to live with the risk of these types of storms, then you're better off living inland. Okay, so how do we rate the destructive power of a hurricane? Well, similar to the Fujita system for the tornadoes, we have a numbering system for hurricanes. And category 1, 2 through 5 is based upon wind speed, and the wind speed is based upon the destruction that it causes. Okay, so you have these effects, and they get more and more severe as the number increases. There are only a handful of category 5 hurricanes that are created each year in the Atlantic. And very often none of those actually make landfall. But when they do, they are extremely destructive. This system was developed a couple of years before the Fujita system, 1969. My guess is that Fujita drew upon the success of the Saffir-Simpson hurricane scale to develop his Fujita scale. Okay, here's a place on the coast that has been hit by a hurricane. Some buildings are destroyed, some are not, right? And most of the damage has occurred from the storm surge. Backwater on the other side of this is probably a barrier island. The other side is more water, and you get lots of flooding. And the roads are covered too. So if you were there for the hurricane, then all you can do is hunker down. More destruction. This is New Orleans after Hurricane Katrina. And New Orleans, if you've ever been to New Orleans, and most people who go to New Orleans want to go to the French Quarter, if you go to a place down close to the Mississippi River called the Café du Monde, is where you go to get hot chocolate, coffee, and beignets. Beignet is a sweet, kind of a puffy biscuit thing. But you'll be sitting there, and under the right conditions, you can look up, you can see the levee that's between you and the Mississippi River, and you might look up there and see a ship going by at 20 or 30 feet higher than you are. The reason for that is a large part of New Orleans is below sea level, and the Mississippi River is at or near sea level. So that ship is up there, and you're down here below the water level. So how does New Orleans survive? Well, they have water pumps. And even during non-storm times, they have to keep pumping water out because it rains a lot in southern Louisiana. So those pumps have to be going all the time in order to remove stormwater or intermittent rainfall. Well, the problem here is that when Katrina came through, it breached one of the levees, actually on the northern side of the city. So New Orleans has to be surrounded by levees to keep the land dry. And the breach occurred on the northern side next to Lake Pontchartrain. And once that was breached, then the water just came rushing in. And the sea level had risen because of the storm surge. So more water than normal would have been sent in, and they lost power. The pumps lost power, and they could not pump the water out of the city. So the place flooded. And those parts of the city that were most vulnerable, the lower elevations, were the hardest hit. This shows you a picture. Centered here is the Superdome in New Orleans. And you can see the winds has ripped large sections of the roof apart. But the Superdome was built at a higher elevation. So it served as a refugee center. People that were fleeing the flood waters in their neighborhoods ended up here at the Superdome. Those who were unlucky enough to get stuck, some people got out before the storm hit. Those were the smart ones. Okay. So I mentioned earlier, as a hurricane moves inland, it rapidly diminishes in strength. It still can do damage, but usually very quickly it downgrades through tropical storm and then to just bad weather, because it is now being decoupled from its energy source, warm water. And there is significant friction for the winds blowing across land, more friction across land than across water, and that sucks energy out of the storm as well. Okay, similar to tornado watch, hurricane watch simply means, and particularly for coastal areas, when there is a threat of a hurricane within 24 or 36 hours. Now, as opposed to a tornado watch, a hurricane watch means that a hurricane has developed and it's heading in your general direction. So you're given a hurricane watch just that so you can make preparations, and further weather bulletins will be issued relative to the hurricane. Now, if you're issued a hurricane warning, that means that your area is going to be hit by the hurricane within the next 24 hours. If that's the case, and you haven't already done it, you need to get out of your area. Go. Okay. Hurricanes are given names. In fact, tropical storms are given names. Tropical storms and hurricanes are blended together for naming purposes. So if you have a tropical storm that's developed, if it's reached the wind speed that's required, then it will be named. And let's see. Beginning in 1953, the National Weather Service began naming storms with female names, right? And that lasted for several years. But in 1979, the National Weather Service started alternating women with female with male names. And they choose, I don't know how they choose them, maybe the random generator of some kind. They choose 21 names. Okay. And those 21 names are assigned to tropical storms as they are identified in the Atlantic. Now, what if you have more than 21 storms developed that year? After the 21st one, the 22nd one is named with the Greek letters. So number 22 will be called alpha. Number 23 will be called beta. And they just go down the line, the Greek alphabet. Alpha, beta, gamma, delta, epsilon, so forth. Now, with this set of names, there's a list that's published, and you can go on the internet and find this list of names for each year. That list of names is recycled every 6 years. So they'll start naming in the 7th year. They'll start with the names that were published in year 1 before. Only they won't always use all of those names. Sometimes, if the hurricane is particularly destructive, they want to preserve that name. It's kind of like a football or a baseball player who's had a particularly stellar career, and they retire the jersey with the number. So from that point on, no other player can have those, that number. They do the same thing for hurricanes. If you have a particularly destructive hurricane, then that name may be retired and never used again. So they'll substitute some other name in there for the next go round. Okay, now we're going to get off of storms and talk a little bit about what's wrong with the atmosphere, right? And in particular, we're looking for pollution And these are not typical contributions that are contributed to the atmosphere from its environment, but these are generally due to the activities of humans. That's what we identify as pollution. Most air pollution is the result of some combustion activity or other industrial process, where byproducts of a manufacturing procedure are in the gaseous phase or maybe suspended phase, and they're discharged into the atmosphere, such as from a coal-fired power plant, or from a steel mill, or from a paper mill, right? If you drive in West Virginia, if you drive past Lewisburg on Interstate 64, you'll come to a place and you'll start smelling some things that smell remarkably. You know that you're close to a paper mill. That's considered pollution, air pollution. This has occurred forever. Humans have been discharging waste into the air, into the ground, into the water for all of human history. And it hasn't been too serious a problem as long as the human population was relatively low. But now we've got over 6 billion people on this planet, and more and more populations are moving from third world to second and first world status. And when that happens, each person generates more waste. That's just the way it goes. That's economics. So the pollution is becoming more serious. The question is, to identify the specifics of the particular pollution and what to do about it. That's the key. Not the fact that it's occurring, but what do you do about it? Is there anything you can do about it? Okay, so examples. In the Industrial Revolution, beginning in the early 19th century, actually it started in England. Burning of coal was very common. There was virtually no wood left. All the wood had been used up. And ready sources of energy were found underground as coal. So they started using coal to provide energy for heating purposes, industrial purposes, whatever the case may be. But this has been going on for a couple of hundred years. And there were times in areas that were thick with coal burning that the whole city was covered, particularly London, was covered in soot. It was, and the earliest examples of smog developed in these areas because there was no control over the burning. Nobody considered what could possibly happen burning all that coal. I mentioned smog. Smog is a contraction of two words, smoke and fog. So the atmospheric conditions have to be just right to produce a fog in your area, and combined with large expulsions of smoke from burning operations. That will produce smog in the classical sense. Now you can get certain types of smog now from a combination of other sources, but you always have the fog and at least some smoke. So what does that mean about the fog part? Well, the fog part means that the temperature at ground level is at or below the dew point. Otherwise, you wouldn't have a cloud on the ground. What can also happen is When this fog forms, you go from vapor phase or gas to liquid. And when that happens, the gas has to give up heat, right, for the fog to form. So where does the heat go? Well, the heat, the air that is heated up by that condensation rises, and you get cool, moist air covered by warm, dry air. That's called a temperature inversion, because normally, remember, in the troposphere, as you go up, the air cools. But in the case of these temperature inversions, you have the cool air near the ground and the warm air over the top, and it traps that cool, moist air down here. And if you have lots of pollution, the pollution stays there too and develops some serious smog and is hazardous to people with pre-existing respiratory problems. Okay, where do we have examples of serious smog? Well, China, Beijing, which used to be called Peking, has experienced some really, really bad smog. China has been, for the past few decades, on a rapid industrialization, which means they're producing a lot more air pollution. And if you don't do something about it, then you run the risk of producing these conditions that generate smog. So this picture is the Forbidden City. This is where the emperors of China used to live. Now it's a tourist attraction. And this is on a clear day, right? Even though you look in the distance and you see some haziness, this is relatively clear for Beijing. On a bad day, when the atmospheric conditions are just right and they trap the pollution in this temperature inversion, then you'll get something that looks like this. That's not just a cloud, that's fog with smoke. That is smog. And notice you don't see as many tourists out in these conditions as you did on the previous slide. All those people, we kind of, I mean, they know better than to get out in that mess. Okay, so diagrammatically, this is what you would expect to see in a temperature inversion. So altitude on the y-axis and temperature on the x-axis. So if we move along here, we see that we can go through, this temperature is cold all the way across. Normally what you would see is with increasing altitude, the temperature would decrease. So we follow this dotted line, and as you get higher and higher and higher and higher, you would expect to see decreasing temperature. That's what's defined as the normal lapse rate for the atmosphere. But in temperature inversion, you get not warm temperatures getting colder, you get cold temperatures near the ground, and then in this region, you have higher temperatures. This is an inverted lapse rate. See, it's got the slope. This is a positive slope. This is a negative slope. And this warm, moist air is trapping the cold, smoggy air underneath. And then once you reach a certain height, you get above that, and then the normal lapse rate resumes. Okay. Those are descriptions, right? So there's nothing unusual there in those items for this slide. There are different types of temperature inversions that can occur. This first one, radiation temperature inversion, results from temperature loss that's radiated from the Earth's surface. Right? So on clear nights, the land surface and the adjacent air close to it rapidly cool. So why is that? The key here is clear nights. When energy is transferred from one place to another, it occurs in one of three different ways. Okay? First way, conduction. Heat is conducted from one place to another. You have to have contact between two objects or two bodies for the heat to transfer. That's conduction. The second one is convection. Convection transfers energy by the wholesale movement of stuff, substance, from one place to another. And the last one is radiation. Energy can be transferred by radiation. In other words, light can take the energy from one place and send it to another place. Okay, this is the one that occurs on a clear night. So, what do you need to transfer energy from one place to another? Heat transfers from high temperature to low temperature, right? That occurs in conduction, to a limited extent in convection, and definitely in radiation. You transfer energy from high temperature to low temperature. So if this is the surface of the Earth and the air that's above it, and this is outer space, okay? Heat is going to be transferred on a clear night because there are no clouds blocking the light transfer from here to here by radiation. This temperature will be, say, in the neighborhood of, I don't know, 20 degrees Celsius, right? So what is that temperature in Kelvin? Remember in chemistry we learned Kelvin? That temperature would be equal to 293 K. Okay, it's just a measurement of temperature. Space, outer space, on average, is at a temperature of 4K. There's a huge difference in temperature between 293 and 4. So the rate of transfer of energy is proportional to the difference in temperature, which would be 289 K to the 4th power. So the rate of transfer is proportional to that difference in temperature to the 4th power. It's extremely efficient. So why did I go to all that trouble? Well, that means that the land surface is going to cool rapidly as the sun goes down and a clear sky appears. In that case, now the ground and the air close to it don't see the sky above them at maybe, I don't know, 0 degrees Celsius or 273. So there's not much difference there. Now that the sun has gone down and there are no clouds in the air, the surface of the Earth sees outer space at 4K temperature. And the transfer is very efficient. Transfer lots of energy. Okay, that's why on a clear night, even in the spring, sometimes you can go out the next morning and look at the windshield of your vehicle. If there was lots of moisture in the air, you can look at the windshield of your vehicle and it's got frost on it. And the temperature through the night never dropped below freezing because the windshield is at a certain temperature and outer space is at a much lower temperature. And so much energy is transferred from your windshield to outer space that it causes the moisture to be deposited on your windshield as frost. Okay. So that's one way that radiation temperature inversion can occur. The air close to the surface of the Earth now is cooled substantially by this radiative heat loss. But the layer of air that's further from the surface of the Earth is not cooled. So you get this cool air on the bottom, warm air on the top. You have an inverted temperature situation. Another form of temperature inversion, subsidence temperature inversion. That happens when a high pressure air mass moves into an area and stops. Okay? So when the dense air that moves into an area, remember, gases are compressible, right? That's one characteristic of gases that is unique. So when the warm air, when the high pressure system moves into an area and there's some landform usually that traps it, then the air behind it keeps pushing. And remember when we studied our gas laws, when air is compressed, it heats up. Okay, that's a combination of Boyle's law and Charles' law. When you compress the gas, it gets hotter. So when it does that, the temperature of the air that moves into this area becomes warmer as it stops, and it's this high pressure air is riding over the top of some other air mass, and that as it gets stopped, it compresses and gets warmer, and that traps relatively cooler air underneath. Typically, these types of things happen where you have landforms that block air movement, like in San Francisco or Los Angeles, where you have mountains on one side and the ocean on the other. This air moves in and it's stopped by the mountains. There's some other forces. It doesn't always ride up the mountains. So the conditions may be right to stop it from moving. So in those conditions, especially over Los Angeles, where you have lots of traffic, lots of automobile exhaust, this air mass will move in, compress and stop, heat up, and trap all that pollution underneath it. That's subsidence inversion versus radiation inversion. Okay, so this cold air wants to sit close to the ground because it's denser than the warm air above it. And any industrial or automobile or domestic generation of polluting gases or particulates are produced, they stay there. They can't move out of that area because there's no mixing. And they tend to build up, right, if you don't do something about it. So what Los Angeles does is when this happens, they just ban all automobile traffic, right? You can't drive your car until the inversion dissipates and the polluted air can be blown away. Then you can go back to normal. Business is normal. These are especially These conditions are especially hazardous for people who have breathing problems, lung ailments, and people who have heart issues. They can kill if the conditions are bad enough and you're not prepared for them. Okay, some major sources of air pollution are combustion of fossil fuels. That's just the fact. They do produce air pollution. Now, what's the nature of that air pollution? That's the $64,000 question. What the EPA, Environmental Protection Agency, has been trying to do for several years is to be permitted by law to label carbon dioxide as a pollutant. Now, human activity does generate carbon dioxide. That's true, but it's not the only source of carbon dioxide. And it's not by any stretch of the imagination a pollutant, because carbon dioxide may be produced by fossil fuel combustion, but carbon dioxide is also food for green plants, right? So what are you going to say? Carbon dioxide is a pollutant? No, it's not. It's excess, but it's normally present in the atmosphere. So in my way of thinking, you can't label CO2 a pollutant. I understand why the EPA wants to label it a pollutant, because it gives it power to regulate it. Right? And that's the kind of power that I don't want to give them. Okay. So this is one type of reaction that will produce carbon dioxide. If you take coke, right? Producing coke from coal for steel production is one way to produce pure carbon, and you burn it in the steel making process or iron smelting process, and it makes CO2. Or if you burn natural gas, CH4 is methane, which is the predominant component of natural gas, combined with oxygen makes carbon dioxide and water. When you put more carbon dioxide in the air, you can also increase acidity. All right? And all you need is moisture. Right? So carbon dioxide plus moisture in the air yields carbonic acid. Okay? That's the same stuff you get in pop. That's what makes it pop when you open the cap. Now, it doesn't stay like that very well, dissolved in water. What it tends to do is decompose into well, actually, it produces a little bit of that, but the reaction wants to go backwards like that. You can produce some of this, but not much. The equilibrium for this reaction is heavily weighted toward carbon dioxide. So that's why when you crack the top of your bottle, it fizzes, because the dissolved carbonic acid would prefer to be carbon dioxide. Right. So that's a bit of a stretch. That's really not the major source of acidity as a pollutant. Most of the acidity produced from human activity is based on sulfur compounds. So maybe we'll get to that in a minute. So what can happen from acid rain? Maybe I better show you that one. Let me see. Let me be sure it's not coming up in a slide. I don't want to steal my own thunder. Yeah, it's coming, acid rain. Okay, we'll get to it in a couple of slides. I know I'm going on for a long time, but these topics are extremely important, so I'm taking a lot of extra time to discuss them. So whatever the form of acidity, acid rain, whether it's from carbon dioxide or from sulfur compounds or whatever, it can have detrimental effects on the environment and even on man-made objects too. Acid rain can accelerate corrosion. For instance, marble statues that were produced back in the 1500s, 1600s, during the Renaissance, are over the years, particularly in modern times, have been subjected to severe corrosion, decomposition due to this acidity. And the reason being that they're made of calcium carbonate. Marble is a form of calcium carbonate. So when calcium carbonate reacts with an acid, you generate a calcium salt and carbonic acid, which generates carbon dioxide. That's why when you put, say if you have, you could do this with lemon juice in a container, and you take a Tums, right, which is calcium carbonate that you eat for stomach acidity, and you drop it in that lemon juice, pretty soon you're going to see bubbles coming up. Those bubbles are carbon dioxide formed by the reaction, but you don't have calcium carbonate anymore. And if you don't have calcium carbonate anymore, that is erosion of your marble statue, for instance. Metals will be corroded more rapidly. Iron, steel, even copper exposed to the environment, if there is acid rain around, will corrode more rapidly. Often what happens with the combustion of various types of fossil fuels, you get incomplete combustion. In other words, rather than going all the way to carbon dioxide when you, say, burn coke, you may get carbon monoxide, right? And that is a hazardous pollutant, right? Carbon monoxide is, what happens is carbon monoxide likes to attach itself to the hemoglobin in your blood cells. Normally, the hemoglobin attaches to oxygen and delivers it throughout your body. And then it's readily released at its destination, which will support the life of your individual cells. But if there is carbon monoxide in your inhale, it combines with the hemoglobin irreversibly. It will not let loose. So your oxygen carrying capacity is reduced, and you basically suffocate on a molecular level if you get enough of carbon monoxide in your system. Here's another type of smog. We mentioned these two previous types due to inversion, radiation temperature inversion and subsidence temperature inversion. That has to do with the temperature differences. But there's also the ability of, there's the smoke part. And the smoke is has a broader definition now. It's not just smoke. There can be other pollutants that are trapped down there in this smog. One of those can be generated by photochemical reactions. In other words, light from the sun will stimulate a certain type of reaction that will produce a pollutant. So if we have various hydrocarbons in the atmosphere and some other pollutants, they react with oxygen in the presence of sunlight. So they need this boost of energy to make those reactions occur. They produce pollutants that are now trapped in that smog. That's photochemical smog. They're very common in Los Angeles. And they can produce various types of compounds, some of which are carcinogens. They produce cancer. They can produce cancer. They have the ability. One of them is ozone. Now, to produce ozone, typically all you need is oxygen and some light source. And you can produce ozone. Now, the good ozone is produced at very high altitudes. And it's an interaction of ultraviolet light from the sun and ozone in the high atmosphere. And ozone is a very efficient absorber of ultraviolet radiation. So it's constantly being regenerated in the upper atmosphere and protects the lower parts of the atmosphere from ultraviolet radiation, which would be deadly to life. But when you produce it at low, near the surface of the earth, where we have to breathe it and living systems have to deal with it, ozone is extremely reactive and it does damage to living systems. Not to mention that it's simply an irritant to lungs and eye tissues. Okay, what are some impurities of fuels that contribute to the pollution? Well, one that's contained in fuels, fossil fuels, is sulfur. The other contaminant is nitrogen, and that's largely contributed not by the fuel, but by the air that's combined with the fuel when you burn it, right? The air is composed of 78% nitrogen and 21% oxygen, and then 1% of other stuff. So when you combine air with fuel, particularly in internal combustion engines, and you put them under pressure, high heat, and ignite them, you necessarily have the potential for reactions with nitrogen and the fuel. So, and you can produce various nitrogen compounds in addition to sulfur compounds that are contained in the fuel, and those are not desirable. You can get nitrogen and oxygen combined in forms that are not desirable. So that's why all cars, all motorized vehicles in the United States, and for many parts of the world, have what we call catalytic converters. They're in the exhaust of internal combustion engines, and they promote, by way of inorganic catalysts, they promote the breakdown of these various nitrogen and sulfur products to simpler, more innocuous products, particularly nitrogen. It will take those compounds of nitrogen and reconvert them to nitrogen gas, and incomplete combustion of carbon compounds will also be further converted into carbon dioxide and water. So we often designate these intermediate compounds with sulfur as SOX. In other words, they're sulfur oxides of some kind. And X can be a number. It could be 1, it could be 2, it could be 3. Sulfur dioxide is common, is the most common result of sulfur and oxygen production upon the burning of fossil fuels. If there is sulfur in the fuel, there are certain areas of West Virginia that produce what's called low sulfur coal. They have very little sulfur in them. There's some, but not much. And these are ideal for production of good, high quality steel. It's called metallurgical coal. Because sulfur in your steel produces some undesirable outcomes. Let's just put it that way. So when you combine sulfur and oxygen, you get sulfur dioxide, okay? Then these sulfur dioxide emissions, if they're not trapped before you release them, for instance, if you're burning coal to produce power, now all modern coal-fired power plants and some older ones are retrofit with the ability to scrub out pollutants from the effluent. And what they'll generally do is use limestone or calcium oxide finely divided and spray it into the exhaust from the power plant when the exhaust is still very hot, so you can get a good reaction, and combine that calcium with the sulfur and make calcium sulfate, gypsum. And then that can be trapped and marketed, actually. Can be sold and return some of the revenue lost in the process of having to capture it. So that's one way that you can keep this sulfur from getting into the atmosphere. Most of the sulfur dioxide pollution occurs in the Northeast, these industrial states. I'm not going to spend a lot of time on that. But where does acid rain come from? It's predominantly from sulfur dioxide. When sulfur dioxide combines with atmospheric oxygen and water, you can either get sulfurous acid, H2SO3, or sulfuric acid, H2SO4. And that can be, when it rains, that can be washed out and collected in bodies of water. And there are some bodies of water in the Northeast that you can see all the way to the bottom of them. They may be 100, 200 feet deep. You can see all the way to the bottom because there's nothing living. It's just pure water that's been acidified to the point where everything that was living in that pond is now dead. Nitrogen can react in the atmosphere along with oxygen to produce nitric acid. Right, so various forms of nitrogen expelled into the atmosphere can be further processed to produce nitric acid. Right, so these are the two primary forms. Carbonic acid is virtually no problem at all. But sulfuric acid and nitric acid can become a serious problem under the right circumstances. All right, I mentioned that already, so I'm going to skip that one. So these are just illustrations of what can happen. Right? You can produce pollutants from internal combustion engines, from other industrial activities, and then those pollutants are brought back down onto the land surface by rain. Acidic precipitation. And remember, very early on in this discussion, I mentioned westerly winds. So in North America, most of the winds coming from the west. So when you blow this stuff into the atmosphere, it's going to move to the east. And any pollutants that are produced in the western parts of the Northeast will be blown into the eastern parts of the Northeast, and they will be most severely affected. Here's a map showing a contour map showing the pH of the rain. Right? Normally, if you dissolve carbon dioxide in water, you will get a pH of about 5.6. That's the result of carbon dioxide saturation in water. That will be considered normal. So most of the western states with pockets of low pH, but most of them are in the 5s. But in the east, when you start to generate more pollutants into the atmosphere, you get more acidified acid rain developing. And it's not because of carbon dioxide now, because carbon dioxide would only make 5.6. So you're looking at nitric acid and sulfuric acid or sulfurous acid as the primary culprits. Okay. In large parts of the United States, this acid rain that falls on the earth is very quickly neutralized. The soils in most of the country have a reasonably high buffer capacity. In other words, they can take these influxes of acid and the pH of the groundwater won't change very much. That's particularly true in the karst regions. Karst regions are those that are derived from limestone basement rock, like southeastern parishes, southeastern counties of West Virginia, like Greenbrier County is a good example, is a karst region. So any acid that falls there is very quickly neutralized by the calcium carbonate base from which the soils are formed. That's why in that region you have lots of sinkholes, because over time water dissolves the calcium carbonate underlying it and produce these caves underneath. Lots of caves over there. And at some point, the underlying cave can no longer support the overlying weight, the burden of the soil and rock above, and it collapses, and you get these sinkholes. So that's a pretty good indication that you're in a karst region. Okay. But for very fast runoff of acid rain, it can affect local streams and bodies of water before the surrounding land has a chance to neutralize the acid. And in those cases, that water collects in ponds and kills everything. Okay. So what are the major sources of air pollution in the, I'm not sure if we're talking about the United States or the world, probably in any industrialized country. Transportation produces lots of carbon monoxide. Okay, that's a problem. Any type of fuel combustion will produce sulfur oxides, which leads to acid rain. Transportation produces unburned hydrocarbons, or incomplete combustion hydrocarbons. There are many industrial processes that produce particulates, like soot, various types of small particles that are generated in the process. Nitrogen oxides are produced primarily by transportation and some stationary sources, industrial sources. Transportation is the largest contributor of air pollution in the country. Some of these particulates that are generated by industrial processes are toxic elements like lead and arsenic. Those are just to name a couple. Now, since the 1960s, with the introduction of the Clean Air Act by the US Congress, air quality has been steadily improving. But it's not perfect. The air quality, with the exception of carbon dioxide, because carbon dioxide is a natural product that we just can't get away with from, because combustion of fossil fuels is the only efficient concentrated source of energy that we have at the moment, aside from nuclear power. So those two sources, nuclear and fossil fuels, are in our future. It's inescapable. If you get rid of both of them, then you end up like Germany is right now. Right? They did that. They tried to go completely green, and their economy is collapsing. And it's in the middle of winter, and their people are freezing because they were stupid. They made very poor decisions. So hang on to fossil fuels and nuclear power for the near future, and let the development of sustainable, renewable sources of energy develop naturally over time, and you will eventually get there. But if you try to force it, then you're going to end up with a disaster. Los Angeles has reduced its smog pollution 75% since the 80s. So that's good. They put in workable measures that would reduce the pollution, because they identified the problem and they identified the solution and enacted it. That is sound public policy. What is not sound public policy is, in the next few slides that I'll demonstrate, what is not sound public policy is to blame climate change on human activity. Right? That's all I'm going to say right at this moment. I'll expound on it later. First of all, what is global climate? Climate, as opposed to weather, is long-term average of weather conditions over a region or over the entire globe. Right? So you're really reaching, you're trying to wrap your arms around the entire world and describe how the climate is changing. That's a really, really tall order. Now, we can look to geologic evidence. Right? Look in the rocks, look in the fossils, and we can find evidence for dramatic climate changes that have occurred over and over and over again throughout Earth's history. Therefore, a very long time, most of the Earth was tropical. We didn't have any what we would consider polar regions with ice caps. And that, we believe, is when most of the fossil fuels were deposited, because productivity was extremely high. Carbon dioxide levels were very high, and that carbon dioxide was being fixed by very active plant life. It was so active that there weren't enough animals to eat it. And it just, when the plants died, they just fell down and they were buried. And that's where we get oil and coal. And there are times in the Earth when the Earth was one giant snowball. It was just a solid layer of ice all the way around. Now, fortunately, at that time, there was still liquid water underneath that ice. And there was microscopic life that was surviving over that period of time. Right? So global climate change is nothing new. And all of these occurred before humans came on the site, before we were here. So that leads me to believe that there really is something else going on. If the global climate is changing, it's probably not due to a major degree to human activity. We've had ice ages, right? In recent history, when humans were here, and there weren't enough humans to actually have an impact. Right? So something else was happening, probably astronomical in nature. Like, how far is the Earth from the sun? Is the tilt of the Earth changed over these eons? How about the energy output of the sun? Has it always been constant like it is now? I mean, has it always been this level? Maybe not. Right? So blaming climate change on humans is, in my estimation, massively irresponsible. We get evidence for climate change from ocean sediment cores too. And they also indicate dramatic climate change over the Earth's history. Now, I put this term generally accepted in quotes because the authors of this slide set said it is generally accepted without quotes by most sciences that the global climate is also being affected by atmospheric pollution. The key here is generally. There are many scientists that will accept the premise that pollution is having an impact on climate. The degree to which that impact is due to pollution is the point of argument. Most scientists don't agree that global climate is seriously affected by atmospheric pollution. That is human-generated pollution, anthropogenic causes of climate change are seriously disputed by many very prominent, very well-respected climate and weather scientists. So, as one of my professors used to say, when you see the results of an experiment or you have someone expounding their position and their research to make a point, think to yourself, it ain't necessarily so. Okay. Maybe human contributions to the atmosphere can affect the radiation balance and impact the global climate. Maybe. There's a very small chance that that could happen. But in my estimation, to say that humans are the major cause of climate change is the height of hubris, that is pride. If you think that human activity can affect a planet on a global scale, then you've got a problem with human pride there. Now, I won't argue against the effect of human activity on local weather, right? That can be fairly well described. Perfect example, Spain. Historical records show that Spain at one time was solid forest from coast to coast, and the climate was much milder. Now, Spain is virtually like the southwestern United States, devoid of trees, a very arid climate, hot and dry. Why is that? They cut all the trees down. So the impact on their local weather, the Spanish weather, is very well documented. But to say that that type of activity can change the whole world's climate is pretty far-fetched. CO2 and other greenhouse gases, particulate emissions, and global cloud cover all affect Earth's albedo. I won't argue with that. Right? What is albedo? It's a measure of how much radiation is reflected from the Earth of the radiation that actually impinges on the Earth. And the Earth generally has a very high albedo. But it has a higher albedo if there are more clouds. So if we generate more clouds somehow, then you can increase its albedo. You can cool the Earth that way. Or if you decrease the number of clouds, you can get more radiation reaching the surface and heat up the Earth more. And there are many other gases that contribute to the greenhouse effect. Many other gases that are even more efficient than carbon dioxide. Methane's, for one, is seriously more intrinsically valued as a greenhouse gas than carbon dioxide. Water. Water vapor is very good. It's not perfect, but it's reasonably good at trapping heat. And what's more than that is there's a whole lot more water in the atmosphere than there is carbon dioxide by several orders of magnitude, right? So focusing on carbon dioxide as the problem is, in my estimation, irresponsible at the very least. So scientists are trying to understand climate change by using various models. So I put the little emoji in here. That's really laughable. And these models that they develop are all buried in computer code. These models are mathematical. They're in computers. They're programs. So you put in information, right? Measurements, information, or just make up information, whatever you want to do. And the model spits out a result and says, oh yeah, the Earth's going to warm by 10 degrees in the next century. The models give scientists the opportunity to compare their theories, to reality, which is not unusual. That's what models are supposed to do. And to use historical data to study the interrelationships between the Earth's atmosphere and other factors. Now, that's a fancy way of saying the models are there to help us try to understand how the Earth's climate works. Now, I won't argue with that. That's a laudable goal. That's a perfectly good research program to get into. The problem arises is when you use those models to induce mass hysteria in the Earth's population. Try to get people to believe that you know something they don't, and that you can predict that their activities are going to destroy the Earth and life on Earth as we know it. So when these climate models are created, scientists generally use one of three different common types. We'll label one as energy balance models. You know, energy that comes into the Earth and energy that goes out, right? And various other transitions in the process. That's one type of model. There's another one called intermediate complexity models, which I don't really understand. So it's there. And those who use them probably understand what they mean. And then the other is general circulation models. So in these, we try to look at the way circulation patterns for these air masses. Where do they go, and what do they do when they get there? I got this information from Columbia University, by the way. So these models, which is typical, right? They try to refine the models. Let's see. I'm looking ahead to see. I don't want to steal my own thunder. Yeah, I do have a slide on it in a minute. So I'll say some more about the models in general. So what are the inputs that we can use to refine the models? Well, you can gather historical climate data, which is typically what they do, from ice cores. You can get infer some things about historical climate using ice cores, because gases are trapped in the ice cores when they are laid down. Tree ring data, they can tell you whether the temperature was particularly cold or warm during a season. Other geological records can also give an indication. And there are many others, like seabed cores, right? Drop a tube down to the bottom of the seabed and pull out a core and section it and see what's in it. That's all I can say about that. But they try to refine their models using historical data. And then once they refine the model, then they try to plug in values and see and predict future changes. Now, the real key is if they predict a future change, and then in the future, you measure something radically different than what they predicted, then I'm going to say that that model is faulty, at the very least. This is what's known as hindcasting. Rather than forecasting, hindcasting. You're using your model to confirm, giving those historical conditions, whether they predict what's already happened. That's hindcasting. And another way to put that is a key to the future is the past. So you're saying if these things happened in the past, then we should be able to predict what's happening in the future based on what we know about the past. There's just one huge problem. Up to this point, none of those models work. They have not been able to predict accurately the changes that we've seen over the past several decades of using these models. And there are a whole host of different models, right? Several dozen of them. Some are getting better at prediction, but they're not there yet. The real problem, in my estimation, is that these refinements that are incorporated into the model, they're designed to match expected outcomes. In other words, if we have a measurement now, then we change the history in order to give us the answer we want. And that's borderline fraud. The other thing about these is when you have a computer model like that, very few people understand how it works. And that includes even some of the scientists that develop the model, right? That's called the black box syndrome. You put something into this black box and it spits out an answer. You don't know what happens inside. I don't like those kind of models. Some of these models have predicted 5 and 10 degrees Celsius rise in average global temperature over a decade. And they missed it by a long shot, right? The actual rise in temperature has been less than 0.5 degree. And that's with wild variations. averaged out. I just use this analogy. Since these models don't work, the image that comes to mind is the Titanic has hit the iceberg and it's sinking. So we send teams down there to patch the holes, right? Right. The holes are the size of a house, and we're trying to patch those holes to save the Titanic. The best thing to do is to get off the Titanic. So here's what you do when any model, and not just climate models, but any model, and models are always developed in conjunction with theories, right? We're trying to say why something happens. So if a model fails under any conditions, whatever conditions they are, you have three options. Number one, modify it. And that's what they've been trying to do over the decades. Modify your model to make it better at predicting outcomes. Okay? Or you can restrict its use. You say, all right, the model only works under these conditions. If you get outside those conditions, it doesn't work. Right? And physicists have been doing that for quite some time. Newton's laws of motion are only good within this narrow range. If the particles get too small, then you have to go to a different theory, like quantum mechanics. If they get too big, like black holes, then Newton's theories fall apart there too. And then you have to go to relativity. So restrict its use. Or for most of them, I think, you ought to just delete them. Just throw them out and start over. I mean, if you really want to predict the outcome of global climate change, then you need to start over. And hopefully be more honest about your predictions and the outcomes while you're doing it. That's a tall order, because there is a ton of money being poured into climate change research. And it's natural. It's human nature to go get it. Scientists are human just like anybody else. So they'll go out there and they'll do the research that the money demands. And very often they produce the results that the money demands also. The problem also is that there are many honest scientists working in this discipline of weather and climate change who are trying to be honest and giving an honest, even skeptical assessment of the situation, conservative by any other estimation. But they're not being heard, because those who stand to gain the most from predicting existential threat to mankind by global pollution and climate change are canceling them. They're using any means possible to shut them up. And that, in my estimation, is despicable behavior. Another way to put it is, for too many of these scientists, money talks and ethics walk. Here's the issue in my estimation. The question is, can we afford to crash the world's economy simply to chase an intangible potential benefit? I would say no. And those who want to do that, I label as climate alarmists. And that's why they couch their warnings in terms of existential threat. The worse you can make the outcome, the more likely you are to get your way. And there's always money involved, always, without exception. Okay. One thing we've learned about the Earth's climate over the past 4+ whatever billion years history is that climate will always change. It has always changed. It will always change. In fact, on average, the climate of the Earth has been relatively stable. If you compare the climate of the Earth to climate on other heavenly bodies that we've measured, Earth's climate is really rock stable, right? As to compared to someplace like Venus or Mars or any of the gas giants. Their climates are not stable. Earth's is stable. At times, Earth was, I mentioned, a tropical rainforest. At times, it was a snowball. If climate change were an existential threat, life would have been extinguished long ago. All right. So the threat of the existential threat argument is fallacious on its face. If you look at the historical record of climate on Earth, life should have been gone a long time ago. What these models never say is why the climate is changing. They point fingers at various pollutants, like carbon dioxide, but they really don't say why their models are worth considering as good predictors. What you should do as a scientist is to investigate and follow the science wherever it leads. It's not unusual over the history of modern science for a scientist here and there to decide that they want a certain outcome. And they design their experiments to give them the answers they want. And some of them even go so far as to fudge their data. Many of those, over time, have either been forgotten in history or they've been caught in the act and their careers are ended immediately, which is what should happen. I mean, that is dishonesty, and we cannot tolerate that in the sciences. Okay, what are some other natural sources of atmospheric pollution? Well, one example, Mount Pinatubo in the Philippines. It expelled massive amounts of particulate matter into the atmosphere. In other words, pulverized rock, and caused a decrease in the Earth's temperature because this material was blown up into the upper stratosphere and circled the globe and blocked light. So the Earth got cooler. Went up to 15 miles into the atmosphere, way up into the stratosphere. And scientists jumped on the opportunity to study the effects of this volcanic eruption. We just recently had another one in the South Pacific that did a similar thing. And I'm sure scientists are investigating that one too. I can't remember the name of it, but it did eject massive amounts of particulates into the upper atmosphere. In addition to these particulates, volcanic ash, sulfur dioxide was pumped into the upper atmosphere. And sulfur dioxide, can undergo reactions that produce sulfuric acid. And it's so high in the atmosphere that it's not going to be brought down by rain. It's going to stay up there for a while. And what it does is, sulfur dioxide and sulfuric acid are very good at blocking radiation. Right? So they do the similar thing to ash. Okay. That ash in the atmosphere gives some beautiful sunrises and sunsets due to the particulates. Now that we have satellites up there in the above the atmosphere, we can make some pretty interesting measurements of the Earth as following these types of events. Various measurements of ozone have been made over the South Pole. And we find that the concentration of ozone over the South Pole has decreased rather precipitously immediately following this 1991 eruption. So we have a correlation there. It might be difficult to prove cause and effect, but it's intriguing. It's definitely worth investigating. Was this eruption the cause of that loss of ozone? Okay. All right. So what other eruptions have occurred? Well, in human history, there was one also in that region, Mount Tambora. In 1815, it blew its top, and it was even bigger than Pinatubo, much bigger, in Indonesia. It took several days for the eruption to occur in April of 1815, and the volcanic ash was blown into the stratosphere, circled the globe. And blocked radiation. In fact, it decreased the temperature, particularly of the northern hemisphere, so much that 1816 didn't have a summer. We had snow in the northern states of the United States in the middle of summer, in June, July, August. And we're pretty sure that it was because of Mount Tambora. All right. No denying, there have been massive, large amounts of carbon dioxide emitted into the atmosphere due to fossil fuel burning over the past century. I remember when I was grade school age, I was interested in the sciences, and the carbon dioxide concentration in the atmosphere was measured at in the neighborhood of around 280 parts per million. Now the concentration is, and that was 60 years ago. Now the concentration is over 400. So we've almost doubled the concentration of carbon dioxide. That's an unmistakable fact, and it's probably due to fossil fuel burning. Now, many scientists agree that this carbon dioxide has contributed to holding in re-radiated heat by the greenhouse effect. Maybe it does alter, it certainly does trap some heat, right? And that's not necessarily a bad thing. because if it weren't for the greenhouse effect by carbon dioxide and by many other compounds in the atmosphere, then the Earth would be a much colder place. And it would not be suitable to modern industrialized life. Our crop failures, for instance, would have a serious impact on human population. So the greenhouse effect is not arguable. It's what's causing it, right? Is just the accumulation of carbon dioxide enough to cause this global warming? No, no way. The US EPA reports that global mean surface temperature has risen around 0.5 degree since the late 19th century. Okay, right? Those measurements are made. Here's an interesting fact. Geological records that have correlated historical, prehistorical carbon dioxide levels in the atmosphere with temperatures has shown that the rise of carbon dioxide in the atmosphere, and there are times in the Earth's history when carbon dioxide level has been 10 times what it is now. Rises in carbon dioxide level have followed temperature increase, not preceded. How about that one? So in that case, geologically speaking, we cannot say that carbon dioxide caused the warming of the Earth. It's the other way around. As the Earth heated up, it caused various processes primarily in the oceans to release more carbon dioxide into the atmosphere. Here's another fact. EPA reports that snow cover in the northern hemisphere and on the floating ice in the Arctic Ocean have decreased. Okay, right? You get fluctuations like that. In addition, sea levels have on average risen by 4 to 8 inches, so maybe 1/2 foot over the past century. Now the question is, are these facts correlated, or are they actually cause and effect? It's fairly easy to show correlation. That's simply a statistical measurement. I can calculate correlation with my eyes closed, one eyeball tied behind my back. Cause and effect is much more difficult to demonstrate. We may get more climate change occurring, but if it's a consequence of CO2, it's going to be very difficult to prove it. So that's why climate change alarmists fall back on existential threat arguments, because they know if they can induce a panic in people and get this Pavlov's dog reaction to anything they tell them, then it's more likely that they can push their agenda through. There are just way too many questions that remain to be answered. And before I acquiesce to a destruction of a modern way of life, collapse of global economy, I want more evidence. Give me more evidence. In other words, prove it. Now, here's an interesting fact. Historical levels have been up to 10 times. CO2 levels have been up to 10 times what they are now. So when did that occur? It occurred during those tropical times when the temperatures were high and plant activity was accelerated due to the increased temperature, right? You know from your study of chemistry in this class that when you increase the temperature, you increase the rate of reactions. So when the Earth was basically tropical and we had all this carbon dioxide in the atmosphere, plants were more active. They were fixing that carbon dioxide into their materials, in their plant materials, and storing it away. And when they died, it got buried, and that's where we got coal and oil. So lots of plant food, high temperatures, it's natural. Plants are more productive. In fact, we can show that if we increase carbon dioxide levels, that productivity of plants increases. That's proven. That's a scientific fact. So increasing carbon dioxide levels is not necessarily bad because we need more food production if the population is going to grow past 6 billion. Okay, if you need more information on National Weather Service activity, here's a good place to start, this link. If you want an honest discussion of climate change, various newsworthy items that occur, then Climate Discussion Nexus is where I go. And that's the end. It took me forever to finish this chapter. I apologize, but there it is. We're done with chapter 20.